Our universe holds a family of 10 suns locked in a single gravitational cage. This is the reality of a decuple-star system, a cosmic configuration so extreme it defies our basic understanding of how stars live together. By the end of this journey, you will know 50 of the strangest truths ever uncovered about these chaotic stellar families. We will explore worlds with 10 suns in their sky and witness stars being hurled into the galactic void. What possible order could exist within such perfect celestial madness? The first confirmed decuple-star system was hiding in plain sight. Astronomers had been observing a bright point of light in the constellation Cassiopeiae for centuries, catalogued as AR Cassiopeiae. For a long time, it was simply considered an interesting but not extraordinary multiple star. The truth was far more spectacular. Through decades of painstaking observation, using the combined power of spectroscopy and photometry, researchers slowly peeled back the layers. They didn't just look at the star's brightness, they dissected its light, watching for the subtle, rhythmic wobbles and dimmings that betray the presence of hidden companions. What emerged from the data was a revelation. That single point of light was not 2 or even 5 stars. It was a family of 10, AR Cassiopeiae, floating some 4,600 light-years away, became the first system to officially shatter our notions of how many stars could possibly share a single cosmic address. The structure they deduced is a masterpiece of gravitational engineering. At its core, astronomers believe, lies a very tight quadruple system, a dizzying dance of 4 stars in a complex, intimate embrace. Around this central chaos, several pairs of binary stars and likely a few single stars trace wide, slow orbits. It is a stellar society with distinct neighborhoods, a sprawling celestial metropolis where a single night might see 10 different sunrises. This confirmation did more than add an entry to a catalog. It fundamentally changed the question. We no longer ask if such systems can exist. Because of AR Cassiopeiae, we now ask how they manage not to tear themselves apart. The existence of such a system immediately forces a breathtaking question. Could planets survive within that 10-star chaos? The answer, against all odds, appears to be yes. The ultimate science fiction scenario is not just fantasy, it is a real, though brutally difficult, possibility in our universe. Theoretical models show that planets could form in the relative calm of a protoplanetary disk swirling around a single star within the larger system, a small island of order in a gravitational hurricane. Some even suggest the potential for a vast, circumsystem disk from which planets might coalesce, orbiting the entire central mass like a distant, lonely sentinel. But the life of such a world would be one of relentless cosmic stress. Imagine a surface where temperatures swing from searing heat to deep freeze not over months, but over days or even hours as different suns rise and set in a frantic celestial ballet. The gravitational tides would be monstrous, stretching the very crust of the planet, likely triggering perpetual, global volcanic upheaval. The greatest danger is a gravitational perturbation, a perfect storm of pulls from multiple stars that could simply punt the planet out of the system entirely, sentencing it to an eternal, frozen drift between the galaxies. And yet, if a world could cling to stability, the sky would be a spectacle beyond human comprehension. Picture a horizon dotted not with one, but with several suns of different sizes and colors, a brilliant orange giant sharing the heavens with a hot blue-white dwarf. True night might never fall, just a dimming into a perpetual multi-hued twilight. Seasons would not be dictated by a single star's tilt, but by the complex, ever-shifting alignments of its many suns. One alignment might bring a period of relative calm and warmth, while another could unleash a barrage of radiation from several stars at once. It is a vision of both terrible beauty and profound loneliness, a world born in the heart of stellar company, yet forever at the mercy of its chaotic whims. This relentless gravitational tension has a violent escape valve. Within the crowded confines of a decuple system, stars don't just dance, they sometimes brawl. The result is a stellar expulsion, a cosmic ejection where one member of the family is flung out into the galactic darkness forever. These are the runaway stars, and some achieve velocities so immense they are called hypervelocity-stars. The mechanism is a devastatingly simple game of celestial billiards known as gravitational scattering. Picture 3 stars in a chaotic, close encounter. 2 of them swing tightly around each other, and in that intimate gravitational embrace, they trade energy. This transfer acts like a slingshot, robbing one star of its orbital speed and supercharging another. The robbed star falls deeper into the system's grip, while the energized one gets a catastrophic boost. If that boost exceeds the system's escape velocity, which in these dense clusters is staggeringly high, the star breaks free. It is shot out like a bullet from a rifle, its trajectory a straight line away from the chaos that birthed it. Astronomers hunt for the evidence of these dramatic divorces. The most telling clue is a star moving at hundreds of kilometers per second on a path that, when traced backwards through the galaxy, points directly to a known complex system, like a forensic line pointing back to the scene of the crime. The decuple system is left forever altered, now a slightly less chaotic nonuple system of 9, bearing the gravitational scars of the explosive event. That ejected star, now a lonely traveler, carries with it the permanent imprint of its violent birth, a silent testament to the fury that exists within a family of 10 suns. The perfect order of a flat, spinning disk is a lie in these systems. Within a decuple star family, the fundamental rule that everything should orbit in a neat, shared plane is often the first casualty of gravitational war. Astronomers peering into young systems have witnessed protoplanetary disks, those vast rings of gas and dust where planets are born, tilted at bizarre angles. They have seen the orbits of stars themselves wildly misaligned, with one binary pair circling each other on a horizontal plane, while another pair dances around them on a vertical track, like gears from different machines forced to mesh. This celestial disarray is a direct product of constant gravitational interference. Each star exerts a torque, a twisting force on the disks and orbits of the others. In a simple system, these forces balance into a flat plane. But with 10 gravitational powers constantly pulling from different directions, no stable alignment can hold. A disk forming around one star gets yanked, twisted, and warped by the relentless tugs of its 9 stellar neighbors, forever preventing it from settling into a calm, unified spin. For any potential planets, this environment is a formational nightmare. A planet coalescing in such a tilted disk would inherit its chaotic inclination. We could see worlds that orbit their star over the poles instead of around the equator, or even planets on retrograde orbits moving backwards compared to their star's spin. Imagine a solar system where the sun rises in the west and sets in the east, not because the planet spins backwards, but because its entire path around its star is reversed. This misalignment shreds the concept of a predictable celestial clockwork, replacing it with a universe where up and down, forward and backward are terms rendered meaningless by the sheer gravitational might of 10 arguing suns. The sky over a decuple world would be a carnival of color. Unlike the uniform glow of our single sun, these systems frequently host stars from across the entire stellar spectrum. You could witness the searing, diamond blue fury of a massive O-type star sharing the heavens with the gentle, ruby glow of a cool M-type red dwarf. Between them might burn a stable, sun-like yellow G-type star and the deeper, orange hue of a K-type giant. This riot of color isn't just a beautiful accident, it's a profound clue to the system's violent history. Such a diverse family suggests these stars were not all born together from the same pristine cloud of gas. Instead, the decuple system likely acted as a gravitational trap, capturing stars of different ages, masses, and compositions as it plowed through its dense birth cluster long ago. It's a stellar zoo assembled by cosmic chance. Alternatively, stars born together can evolve at wildly different speeds. A massive star might blaze through its life in just a few million years, swelling into a red giant while its lighter siblings are still in their stable yellow infancy. The result is the same, a single point of light that, when magnified, resolves into a mosaic of contrasting stellar fires. For any hypothetical planet, this color carnival creates a radiation environment of terrifying complexity. The planet would be bathed in a shifting blend of ultraviolet fury from the blue stars, gentle visible light from the sun-like ones, and intense infrared from the red dwarfs. A single orbit could carry a world through zones dominated by different stars, subjecting its atmosphere and any potential chemistry to a relentless, changing barrage. It is a beautiful and brutal paradox, a painter's palette of light that could also be a recipe for cosmic sterilization. That beautiful color carnival comes with a lethal price. Among the gentle red dwarfs and brilliant giants in a decuple system, a hidden danger brews, one capable of sterilizing entire worlds in an instant. These crowded stellar families have been identified as super flare factories, cosmic engines for generating bursts of energy so violent they defy comprehension. The key ingredient is proximity and chaos. When stars, particularly magnetically active red dwarfs, orbit each other extremely closely, they often become tidally locked. This means the same face of each star perpetually stares at its partner, just as our moon always shows Earth the same side. This tidal locking, combined with the relentless gravitational squeezing from multiple neighbors, stirs the stellar interiors into a frenzy. It amplifies their magnetic dynamos, twisting magnetic field lines into knots of unimaginable tension. Eventually, these fields snap. In a cataclysm measured in minutes, a star can unleash a superflare, an eruption thousands of times more powerful than the largest solar flare ever recorded from our own sun. The energy released is staggering, equivalent to billions of our most powerful nuclear detonations all exploding at once. For astronomers, detecting these events is a matter of watching for the impossible. All sky survey telescopes like TESS stare at vast patches of space, monitoring the brightness of thousands of stars. In a decuple system, they don't just see a single star spike in brightness. They witness the entire complex point of light flare as a single unit, brightening by several magnitudes as one or more of its constituent stars detonates. It is a system-wide tantrum, a flashbulb going off in the heart of stellar chaos. For any fragile atmosphere or nascent chemistry on a nearby world, this is an apocalyptic constant. A single such flare would blast away years of atmospheric development, flooding the surface with a killing tide of X-rays and ultraviolet radiation. In a decuple system, where such events could be weekly or even daily occurrences, the concept of a stable climate vanishes. Life would need to be not just hardy, but something utterly alien, perhaps buried deep in planetary ice or rock, forever hiding from the angry skies of its 10 parent suns. The violent energy of superflares hints at a deeper, invisible tension holding these stellar families together. Astronomers mapping the frantic orbits within candidate decuple systems have stumbled upon a gravitational ghost. The math simply does not add up. By meticulously tracking the speeds and paths of the visible stars, scientists can calculate the total mass required to keep them all bound. Again and again, they find a chilling discrepancy. The combined mass of the 10 shining suns is not enough. A significant portion of the gravity, sometimes a staggering amount, is coming from something they cannot see. This is the mystery of the missing mass, a dark signature at the heart of stellar chaos. What invisible anchor keeps this frenzied dance from flying apart? The first suspect is a swarm of brown dwarfs. These are failed stars, objects too massive to be planets but not massive enough to ignite sustained nuclear fusion in their cores. They form like stars but then fade into a cold, dark gloom, emitting only a faint infrared whisper. A decuple system could be harboring dozens, even hundreds of these shadowy orbs, their collective gravity weaving an unseen web that corrals the brighter stars. Another, more dramatic possibility is a central black hole. This could be the remnant of a past catastrophe, a stellar merger or collapse from the system's violent youth. Sitting at the gravitational heart of the chaos, even a relatively small black hole with the mass of just a few suns would exert a commanding pull on everything around it. It would be the silent conductor of this 10-star orchestra, an invisible maestro ensuring the music, however chaotic, never stops. A third explanation is less exotic but equally vast: enormous reservoirs of cold gas and dust that have avoided collapsing into stars. These dark, frigid clouds could hold many times the mass of the visible stars, yet remain virtually transparent to our telescopes. Each of these answers paints a profoundly different picture of the system's architecture and history. A brown dwarf swarm suggests a system that formed with an abundance of material that just missed becoming true stars. A central black hole implies a past of unimaginable stellar violence. Vast cold clouds point to a system still under construction, or one that is strangely inefficient at building suns. Until we can peer deeper into the dark, this missing mass remains one of the greatest puzzles, the hidden hand that may ultimately decide whether a family of 10 suns endures for eons or tears itself apart tomorrow. The gravitational intimacy within these stellar families creates connections more literal than we can see. In the closest binary pairs of a decuple system, the stars don't just orbit each other, they begin to share their very substance. The immense tidal forces, stronger than anywhere else in the galaxy, can stretch a star's outer atmosphere until it breaches a point of no return called the Roche lobe. This is the star's gravitational territory, the space where it can hold onto its own material. When a star swells or is pulled so close that its atmosphere spills beyond this invisible boundary, something spectacular happens. The stolen gas does not simply float away. It gets funneled by the companion's gravity, forming a vast, arching stream of superheated plasma, a tidal tail that creates a temporary bridge of fire between the two suns. You are witnessing a stellar artery, a direct transfusion of matter from one cosmic body to another. This process, called mass transfer, transforms both stars. The donor star loses a part of itself, often shrinking and cooling in the process. The recipient star gains this fresh fuel, which can ignite new nuclear reactions on its surface or cause it to swell and brighten. But the most dramatic outcome occurs when the receiving star is a white dwarf, the incredibly dense, Earth-sized corpse of a Sun-like star. As hydrogen-rich gas from its companion flows across the tidal bridge and piles onto the white dwarf's searing hot surface, pressure and temperature build to a catastrophic threshold. Suddenly, the entire accumulated layer of stolen fuel undergoes a runaway thermonuclear explosion. From our distant vantage point, we see what's called a nova, a star that appears to flare into existence where none was visible before, outshining its entire system for a brief, brilliant period. This is not a star destroying itself, but a star violently processing a gift from its overly intimate neighbor. Astronomers detect these plasma bridges not with pictures, but by reading the stories written in starlight. Using a spectrograph, they break the system's combined light into a rainbow, searching for specific dark lines that indicate the presence of elements like hydrogen or helium. In a stable star, these absorption lines are fixed, but in a system with a tidal tail, they see something bizarre. The lines are not just dark, they are blurred and smeared. This smearing is a Doppler shift in action. One side of the plasma stream is flowing toward us at incredible speed, blue shifting its part of the absorption line. The other side of the stream is flowing away, redshifting its signature. The result is a single, dark line stretched into a broad, shallow trough in the spectrum, a direct fingerprint of gas screaming in both directions along that celestial bridge. It is a silent, spectroscopic scream of gravitational theft, proving that in the heart of a decuple system, stars are not merely neighbors, they are participants in a continuous, violent exchange of their very essence. That silent, spectroscopic scream of stellar theft could be a prelude to the ultimate cosmic explosion. The gravitational bonds within a decuple system are so unimaginably strong they can potentially survive a supernova. This leads to one of the most staggering possibilities of all, that among the 10 suns, one may not be a sun at all, but the spinning, hyper-dense corpse left behind after a star's catastrophic death, a neutron star or its beacon-like variant, a pulsar. The scenario begins with one of the system's original members being a true behemoth, a massive star many times heavier than our sun. It lives fast and burns furiously, destined for a short life. When its core finally collapses, it unleashes a supernova explosion of near unfathomable power. In a simple binary, such a blast would almost certainly blow the companion star away, severing the gravitational connection forever. But in the intricate web of a decuple system, the story is different. The doomed star is not just bound to one partner, it is locked in the collective gravity of 9 others. This creates an anchor of staggering mass. When the supernova erupts, the explosion is asymmetric. The dying star's core is kicked violently in one direction. Yet, if the remaining gravitational pull from its 9 stellar siblings is strong enough, that kick might not be sufficient for total escape. The newborn neutron star, a city-sized object containing more mass than our entire sun, could be retained, left to whirl through the system's chaotic lanes on a new, wild trajectory. Finding such an object, however, is a hunt for a ghost with a heartbeat. Astronomers search for the telltale sign, a lighthouse beam of radiation sweeping through space. A pulsar is a rapidly spinning neutron star with intense magnetic fields that channel radiation into narrow beams from its poles. If one of those beams periodically sweeps across Earth, we detect it as an exquisitely precise radio pulse, a cosmic metronome ticking with millisecond regularity. In a decuple system, they would listen for that perfect rhythm emerging from the optical glare of the multiple stars. Alternatively, they might look for the X-ray glow of violent accretion. If the pulsar has a close stellar companion, it can rip gas from its neighbor's atmosphere, funneling it onto its surface at nearly the speed of light. This process generates searing X-rays, a high-energy fingerprint of a vampire star at work. Discovering a pulsar in this celestial maze would be a scientific windfall. Its pulses would serve as the most precise clock imaginable. By tracking the subtle delays and advances in its rhythm as it moves through the system's tangled gravity wells, astronomers could map the orbits and masses of all the other stars with unprecedented accuracy. It would be like placing a hyper-accurate GPS tracker in the heart of the chaos. The partnerships it could form are mind-bending. We could have a pulsar locked in a tight, whirling dance with a sun-like star, a pairing of a dead stellar ember and a living sun. That binary pair might itself orbit another pair of stars, creating a triple system with a pulsar at its heart, and that triple could be just one component in the wider decuple ballet. It is a Russian nesting doll of gravitational relationships, with a dead star's relentless pulse keeping perfect time over a graveyard it helped create, a testament to bonds so strong they outlast stellar death itself. That pulsar's perfect clockwork is a rare survivor, but not every stellar encounter in this chaos ends with such elegant order. Sometimes the gravitational shoving from 9 neighbors pushes 2 stars into a terminal embrace. This is the origin of the zombie star, a cosmic revenant that should not exist. Astronomers call them blue stragglers. Picture a crowded stellar cluster where most stars are aging gracefully, cooling into red giants or fading into dim dwarfs. Yet, scattered among them are a few brilliant, hot blue stars, shining with the fierce energy of youth. They are stragglers, lagging behind the evolutionary clock of their peers. Their secret is not youth but resurrection. They are the product of stellar cannibalism, two older, cooler stars that have been forced together by the relentless gravitational tides of their crowded environment. In a decuple system, such a forced marriage is almost inevitable. A close binary pair already dancing tightly can have its orbit destabilized by a gravitational nudge from a passing third star. This nudge shrinks their orbit, drawing them closer and closer until their outer atmospheres touch. What follows is not a destructive explosion, but a violent merger. The two stars spiral into each other, their gases mixing in a turbulent, fiery whirlpool. When the chaos settles, a new, single star is born. It is more massive and hotter than either of its progenitors, its fresh hydrogen fuel stirred from their combined cores reigniting a fierce blue-white fire. This stellar zombie now shines with a borrowed, violent youth, its true age betrayed only by the chemical fingerprints of its dual origin deep within its spectrum. Its presence is a gravitational wild card. This new, heavier star now exerts a stronger pull on its 8 remaining siblings, potentially destabilizing other delicate orbits and setting the stage for future collisions or ejections. It is a phoenix born from a crash, a brilliant blue anomaly that is both a product of the system's violence and a new source of its future chaos. Amidst the stellar brawls and violent mergers, a whisper of perfect mathematical order somehow survives. Astronomers have found that within the broader chaos of a decuple system, small groups of stars can lock into an exquisite orbital synchrony called a resonance. Picture 3 stars orbiting a common center, not in random periods but in a precise celestial rhythm. For every 4 orbits the outermost star completes, the middle star finishes exactly 2, and the innermost star finishes exactly 1. Their orbital periods exist in a clean 4:2:1 ratio, a gravitational harmony that repeats with clockwork perfection over centuries. This resonance is not a quiet agreement, it is a powerful stabilizing force. When the stars align at their closest points, their gravitational tugs reinforce each other in a consistent, predictable pattern. Instead of delivering random, destabilizing kicks, these periodic pulls actually shepherd the stars, keeping their orbits regular and protected from the more chaotic influences of the other stars further out in the system. It is a pocket of calculated peace within the storm. How can such delicate harmony arise from initial chaos? The answer lies in the system's infancy, within the cradle of the gas-rich nebula where it was born. In those early days, the young stars were not moving in a vacuum. They were plowing through a thick soup of leftover gas and dust. This created a powerful drag force like wading through deep water. As the stars lost energy to this drag, their orbits slowly shrank and circularized. During this slow migration, they naturally fell into step with each other. If one star's orbital period came close to a simple ratio with another's, their repeated gravitational nudges at the same orbital phase would amplify, locking them into that resonant beat permanently, even after the gas disk dissipated. It is a beautiful paradox, the very forces of friction and drag that might seem to promote disorder instead sculpting a lasting, musical order. This resonant chain is a gravitational melody, a few clear notes played on a cosmic scale, enduring even as the rest of the 10-star orchestra continues its furious, discordant symphony. Those resonant chains exist within a far larger architectural blueprint, one written not in starlight but in dust. Peering into the heart of a decuple system with infrared eyes, astronomers have unraveled a dust enigma. They find not a single, unified disk, but a series of them, like nested celestial rings stacked at bizarre angles around different groups of stars. It is a system with multiple construction zones, each operating under a different set of gravitational rules. Closest to the tightest binary pair, there might be a thin, searingly hot disk of fine dust and gas, glowing fiercely as it is constantly vaporized and replenished by the stellar winds of its 2 furious suns. Further out, encircling a wider quadruple subsystem, a broader, cooler disk of pebbles and planetesimals could spin, its material constantly jostled by the complex gravity of its four masters. And at the very outer fringes, where the light of all 10 stars is but a faint collective glimmer, a vast, frigid ring of icy debris might stretch for billions of miles, a relic of the system's earliest days. These disks are the leftover building blocks, the construction materials that never quite became planets. They glow not in visible light, but in the infrared, radiating the faint heat they absorb from the distant suns. Their presence and their bizarre, misaligned geometries are a direct map of the system's gravitational forces. Every close stellar flyby, every gravitational nudge from a passing sibling stirs this dust like a spoon in a cosmic soup. It sculpts the disks into warped shapes, truncates their edges, and creates bright clumps and dark gaps where material has been either gathered together or violently scattered. The warm inner disks hint at where planet formation was attempted and likely thwarted, a continuous cycle of assembly and destruction. The vast outer debris ring tells a different story, one of ongoing bombardment. Within that cold expanse, leftover planetesimals, the failed cores of worlds, still collide. Each impact crushes rock and ice into fresh clouds of fine dust, replenishing the ring and creating a detectable infrared glow. Listening to these systems with radio telescopes, astronomers can sometimes hear the whisper of these collisions, the gentle rustle of gravel-sized particles constantly smashing together in the dark. This layered dust architecture reveals the decuple system not as a simple ball of stars, but as a structured, if chaotic, cosmic ecosystem with distinct neighborhoods, each with its own history of creation and ruin, all bound together by the invisible threads of gravity. Buried within that chaotic light is a cosmic clockwork so rare it borders on the miraculous. In the vast sprawl of a decuple system, with its wildly tilted orbits, the chance that any of those 10 suns align perfectly from our distant viewpoint is astronomically small. Yet, against all odds, a few of these stellar families are oriented just right. From our solar system, we see them edge on, and the result is a celestial ballet of shadows called an eclipsing decuple. The light we receive from that single, complex point is not steady. It flickers and pulses in a pattern of breathtaking complexity. This is the light curve, a graph of brightness over time, and for these systems it looks less like a chart and more like the frantic scribble of a madman. A deep, prolonged dip might signal a large, cool giant star sliding in front of a smaller, hotter companion, blotting out its fierce blue light for hours. Minutes later, a sharp, V-shaped plummet could reveal a pair of tightly orbiting dwarfs crossing each other in a quick, precise transit. Then, just as the light seems to recover, a third, shallower dimming begins as another distant binary pair within the system starts its own eclipse, overlapping the first. The pattern never truly repeats in a simple cycle because you are not watching one clock, but 10 interconnected timepieces all ticking at different speeds. This chaotic photometric fingerprint is the master key to unlocking the system's secrets. Each distinct dip in the light curve is a shadow play that reveals precise information. The depth of the dip tells astronomers the relative sizes of the eclipsing stars. The shape of the dip, whether it is flat-bottomed or rounded, reveals details about their atmospheres and how sharply defined their edges are. The timing between dips, once untangled from the overlapping patterns, gives the exact orbital periods of each pair. By patiently observing this flickering starlight for years, sometimes decades, astronomers can perform a feat of cosmic forensics. They slowly disentangle each individual eclipse signature, building a dynamic model of the entire family. They can say with growing certainty that dip number 7 belongs to the close binary orbiting the central quadruple every 3.2 days, and that the broad, shallow dimming every 400 days is caused by a distant, single star passing behind the collective glare of the inner chaos. It is a painstaking puzzle where every piece is a shadow, and the final picture is a precise map of orbits, sizes, and relationships for 10 different suns, all deduced from the simple, ancient act of watching a light flicker and fade. The flickering light curves reveal a map of celestial mechanics, but they also force us to confront the ultimate cosmic question: could anything truly live in that chaos? The very idea of a habitable zone, that Goldilocks region around a star where liquid water could exist on a planet's surface, becomes a cruel joke in a decuple system. Here, it is not a calm, stable band, but a tormented volume of space that warps, stretches, and vanishes with the ever-shifting alignments of 10 different suns. Imagine a world whose orbit carries it on a wild roller coaster through this gravitational labyrinth. For a brief, glorious window, it might find itself perfectly positioned between two of its gentler suns, enjoying a double dose of temperate warmth. But as the orbits continue their relentless march, that same world could soon be flung inward, broiled under the combined glare of 3 close stars, or cast outward into a deep freeze illuminated only by the dim, ruby light of a distant red dwarf. The climate swings would not be measured in millennia, but in years, months, or even days. The very ground would tremble with gravitational tides, a constant planetary quake triggered by the competing pulls of multiple massive bodies. And piercing this unstable environment would be the random, sterilizing blasts of superflares from the system's magnetically furious stars, stripping away atmospheres and scouring surfaces with lethal radiation. This is a recipe for a perpetual planetary apocalypse, a cycle of scorching, freezing, and irradiating that seems to leave no room for the delicate, persistent chemistry we call life. Yet, against this bleak portrait, a sliver of possibility emerges from the shadows quite literally. While a rocky planet orbiting a star directly may be doomed, a large moon orbiting a gas giant could carve out a bizarre niche. Picture a massive Jupiter-like world, itself on a chaotic path through the stellar menagerie. This gas giant would have no solid surface to scorch or freeze, but it could shepherd a family of moons. One of those moons, if it were icy and large enough like Jupiter's Europa or Saturn's Enceladus, might find salvation in its own captivity. Locked in a tight, tidal embrace with its giant planet, the moon's interior would be constantly kneaded and heated by gravitational friction. This internal warmth could maintain a vast, global ocean of liquid water deep beneath a miles-thick crust of ice. That icy shell would then act as a perfect shield, protecting that hidden sea from the violent radiation and temperature extremes of the chaotic sky above. In this scenario, the moon's parent planet becomes both its jailer and its protector, its immense gravity providing the heat for life while its bulk blocks the deadly flares. The surface of such a moon would be a frozen, cratered wasteland under a terrifying sky of multiple, shifting suns. But far below, in eternal darkness, in waters warmed by the moon's own flexing heart, the conditions for life might persist in serene isolation. It is a haunting thought that the only conceivable abodes for biology in a system of 10 suns are not sunlit gardens, but lightless, subsurface abysses, forever hidden from the very stars that gave them form. Buried within the chaotic orbits of these 10-star families is a future symphony of invisible ripples, the same gravitational dances that fling stars away and force stellar mergers are also forging the universe's most perfect cosmic bells. As the system ages over billions of years, its most massive stars will die first, exploding as supernova and leaving behind ultra-dense remnants, white dwarfs, neutron stars, and even black holes. In a simple star system, these dead stars might drift apart, but in the crowded, dynamic environment of a decuple system, something extraordinary happens. The relentless gravitational nudges from the living stars can herd these stellar corpses together, pushing them into incredibly tight binary pairs. Imagine 2 city-sized neutron stars, each heavier than our Sun, orbiting each other so closely that their year lasts mere minutes. They are the ultimate product of this celestial pressure cooker, a binary of compact objects spiraling ever closer, destined to collide. This fate makes decuple systems gravitational wave factories. Those spiraling pairs of dead stars do not orbit in silence. As they whirl at a significant fraction of light speed, they churn the very fabric of spacetime itself, sending out ripples called gravitational waves. These waves are incredibly faint, a stretching and squeezing of space on a scale smaller than an atom. For decades, we have detected the violent, final chirps of such collisions from distant galaxies with observatories like LIGO and Virgo. But the future holds an even more sensitive ear. The space-based observatory LISA, a constellation of 3 spacecraft flying in a giant triangle millions of kilometers apart, is designed to listen to a different part of the gravitational wave spectrum. It will hear the lower frequency hum of these binaries not in their final, catastrophic seconds, but in their slow, centuries-long in-spiral. A decuple system could host several of these humming binaries at once, each with its own unique tone based on the masses of its components, creating a complex chord of impending collisions. The beauty of this gravitational chirp is that it carries a pristine record of its origin. By analyzing the subtle changes in the wave's frequency and amplitude as the objects spiral together, scientists can read the story of their birth. The waves will reveal the exact masses and spins of the neutron stars or black holes. More astonishingly, they can trace the history of the dynamical interactions that created them. Did this binary form from 2 stars that were born together and survived their supernova? Or was it assembled later in life when 2 solar remnants were gravitationally captured and bound by a close encounter with a 3rd star? The gravitational wave signal holds subtle fingerprints that can distinguish between these histories. This means that by listening to the hum from these systems, we are not just detecting exotic objects, we are conducting archaeology. We are decoding the gravitational environment that forged them, offering a census of these extreme stellar families across the Milky Way that is completely independent of the flickering, complex light we see. In the silent darkness between the stars, the ghosts of these chaotic systems will sing their creation stories for billions of years, and soon we will have the instruments to finally understand the tune. That gravitational hum from dead stars is the final chapter of a story that began in a stellar nursery. These extreme families of 10 suns are rarely cosmic loners. More often, they are found as the brilliant, dense hearts of sprawling open star clusters or loose stellar associations, drifting together through the galactic disk. This is no coincidence, it is a direct clue to their violent and competitive birth. The process begins inside a giant molecular cloud, a cold, dark nebula light years across, pregnant with the raw material for thousands of stars. As gravity begins to fragment this vast cloud, it does not collapse uniformly. Instead, it shatters hierarchically, breaking into smaller clumps, which themselves fragment into even denser knots. In the richest, most turbulent regions, the competition for gas is fierce. The densest subclump, the one that wins the gravitational battle, draws in the most material and fragments not into 1 or 2 stars, but into a whole litter of stellar embryos, packed into a volume of space that would barely reach from our sun to the next star over. This is the proto-decuple system, a seething nest of young suns all fighting for fuel in a cosmic free-for-all. The evidence for this kinship is written in their motion. Astronomers measure the subtle, sideways drift of stars across the sky, called proper motion, and their speed toward or away from us, the radial velocity. When they study a suspected decuple system, they often find its complex point of light shares an almost identical proper motion and radial velocity with dozens, sometimes hundreds, of other stars in its immediate vicinity. They are all moving in lockstep, a family traveling together through the galaxy. The decuple system is simply the brightest, most massive, and most gravitationally bound knot at the center of this extended stellar family. It acts as the anchor, the gravitational keystone holding the memory of their shared origin. This kinematic link transforms our understanding. A decuple system is not a freak accident. It is the natural, extreme endpoint of hierarchical star formation in the most fecund stellar nurseries. It is the overachieving core of a much larger clan, a reminder that where stars are born in crowds, the strongest gravitational players will seize the most resources and forge bonds of unimaginable complexity, forever marking themselves as the crowded heart of a drifting stellar city. The chaotic light from these 10-star families is not just a mess, it is a symphony. Decuple systems are treasure troves of variable stars, celestial objects whose brightness changes in predictable or dramatic ways. Within a single, crowded point of light, you can find nearly every type of variable star known to astronomy. There are the eclipsing binaries whose regular clockwork dips we already explored. But alongside them, you might find pulsating stars like Cepheids or AR Lyrae, ancient giants that rhythmically swell and shrink, brightening and dimming as their outer layers breathe in and out over days or weeks. There could be eruptive cataclysmic variables where a white dwarf cannibalizes its companion in bursts of violent brilliance. And there are rotating spotted stars similar to our Sun, but with monstrous star spots that, as they turn in and out of view, cause the star's light to rise and fall like a slow cosmic heartbeat. Having so many variable stars packed into one system creates a combined light signal of mind-boggling complexity. It is not just one rhythm, but dozens of overlapping rhythms, all playing at different tempos and volumes, from the quick staccato of a tight binary to the slow, deep bass note of a long-period giant. To make sense of this cacophony, astronomers turn to a powerful mathematical tool called Fourier analysis. Think of it as the ultimate audio filter for starlight. This technique can take that tangled, flickering light curve and decompose it, separating the blended signal into its individual periodic components. It identifies each distinct frequency, each repeating pattern hidden within the noise, that faint 3-day pulse buried under the glare of a 5-hour eclipse can be isolated and measured. This mathematical disentangling is absolutely essential for confirming the stellar count in these systems. By identifying the unique fingerprint of each variable star, Fourier analysis helps prove that a specific dip or pulse belongs to a distinct celestial body, building the case for a 9th or 10th member. This turns the entire decuple system into a natural laboratory. Instead of studying one type of variable star in isolation across the galaxy, astronomers can observe multiple types interacting within the same extreme gravitational environment. They can watch how the pulsation of a Cepheid might be subtly altered by the tidal pull of a close binary neighbor, or how the eruption of a cataclysmic variable might be triggered by a gravitational nudge from a passing star. It is stellar evolution and variability research, all contained within one densely packed, brilliantly chaotic celestial cage. The symphony of variable stars sometimes plays a note of profound intimacy. Deep within the gravitational tangle of a decuple system, astronomers occasionally find a pair of stars locked in a permanent, skin-tight embrace. These are overcontact binaries, and they defy everything we expect about personal space in such a chaotic environment. In a typical binary, two stars orbit each other with a clear separation, like dancers holding hands at arm's length. But in an overcontact system, the stars are so phenomenally close that their outer atmospheres have merged. They no longer have two distinct spherical shapes. Instead, they are stretched into a single, shared envelope of superheated plasma, forming a bizarre celestial structure that looks like a glowing peanut or a figure 8. The most common type are W Ursae Majoris stars, named for their prototype. These are contact binaries where both stars, often similar in temperature, are literally touching, their surfaces connected by a searing bridge of flowing gas. Material is constantly exchanged through this stellar umbilical cord, creating a single, thermally connected system with two hearts beating inside one bloated, luminous body. Finding such an exquisitely delicate configuration within the violent shoving match of a 10-star system is a profound puzzle. The gravitational perturbations from 8 other massive bodies should, in theory, be catastrophic for such a tight couple. A close stellar flyby or a resonant gravitational kick should either tear the pair apart entirely or, more likely, force them into a collision and merger long ago. Their continued existence, therefore, tells a story of either remarkable luck or surprising protection. One possibility is that this intimate pair formed that way from the very beginning, a rare twin embryo in the stellar nursery that coalesced already in contact, their bond forged before the rest of the chaotic system fully assembled around them. The other, more intriguing idea is that the system's very chaos is what shelters them. The complex gravitational field of a decuple system is not uniform. It has zones of relative calm within the storm, stable pockets in the orbital dynamics where certain configurations can survive. This overcontact binary might occupy such a gravitational sweet spot, its orbit synchronized in such a way that the external tugs from its siblings mostly cancel each other out, leaving their intimate dance undisturbed. It is a cosmic paradox, a pair of Siamese twin stars whose fragile union is somehow preserved by the very pandemonium that should destroy it. A single, quiet whisper of connection enduring at the heart of the shouting crowd. That intimate, shared envelope of an overcontact binary hints at a deeper, hidden history written in starlight. When astronomers point their spectrographs at the individual members of a decuple system, they expect a certain uniformity. Stars born from the same giant molecular cloud should be chemical siblings, sharing nearly identical proportions of elements like hydrogen, helium, iron, and silicon. Yet sometimes the data reveals a startling anomaly. One star in the family will show a bizarre and significant overabundance of specific heavy elements like barium, strontium, or the rare earth element europium. This is not a subtle difference, it is a glaring chemical signature that marks this star as an oddity among its kin. This phenomenon is called chemical pollution, and it is the definitive evidence of a cosmic crime scene, a stellar murder that happened billions of years ago. The polluting elements are known as S-process elements, forged in the slow neutron capture processes that occur deep within the hearts of certain aging stars. The culprit is a star that is no longer there. In the system's distant past, one of the original members, a star slightly more massive than our Sun, reached the end of its stable life. It swelled into a red giant, then entered a brief but spectacular phase called the asymptotic giant branch. During this stage, the star becomes a cosmic alchemist. In its deep, convective layers, neutrons are captured by iron nuclei, building them up atom by atom into heavier elements like barium and europium. These newly forged metals are then dredged up to the star's surface by powerful currents. Here is where the crime occurs. If this aging giant was in a close binary partnership, its swollen atmosphere would have easily spilled over onto its companion star. For millions of years, a torrent of metal-rich gas, a stellar bloodstream carrying the products of advanced nuclear fusion, flowed across the gravitational bridge between them. The receiving star was bathed in this exotic material, incorporating the heavy elements into its own outer layers. Then the donor star completed its evolution. It shed its remaining outer layers as a beautiful planetary nebula and shrunk down to a tiny, dense white dwarf. That white dwarf may still be there, a faint ember orbiting its polluted partner, or it may have been lost in a later gravitational encounter, ejected from the system entirely. What remains is the polluted star shining brightly. Its spectrum is a permanent tombstone, every photon of light carrying the enhanced signature of barium or europium is a direct message from a ghost. We are not just looking at 10 stars, we are seeing the preserved material of an 11th, a stellar ancestor that lived, died, and donated its essence to a sibling. This transforms the decuple system into an archaeological dig site. By reading the precise levels of these exotic elements, astronomers can estimate the mass of the original donor star and even the duration of the mass transfer event. It is forensic astronomy proving that these families are not static but dynamic graveyards, where the dead continue to shape the living in the most literal way imaginable. The chemical tombstone of a dead star is a permanent scar, but some wounds are still bleeding. The gravitational bonds holding a family of 10 suns are strong, yet they are not invincible to an external threat. Computer simulations reveal a chilling scenario, the flyby catastrophe. A decuple system, for all its internal chaos, orbits peacefully within the galaxy until a much larger gravitational force passes too close. This intruder could be another star cluster, a rogue giant molecular cloud, or even a dark matter subhalo, a massive but completely invisible knot of dark matter. As this interloper swings by, its immense gravity creates a powerful external tide. This is not a single pull, but a stretching force. The side of the decuple system closest to the intruder feels a stronger tug than the side farther away. This tidal force injects a massive surge of energy into the entire stellar family. The effects are immediate and devastating. The system's outermost, most loosely bound stars receive the biggest jolt. That extra energy can exceed their gravitational attachment to the group. In a single, silent event, these stars are unbound. They don't get a dramatic slingshot ejection from an internal brawl. They simply drift away, their connection severed by an outside hand. Meanwhile, the inner core of the system experiences a different kind of violence. The tidal injection can have the perverse effect of tightening the orbits of the stars closest to the center. Their paths become smaller, faster, and more elliptical, pushing them into dangerously close proximity. This sudden compression is a recipe for disaster, dramatically increasing the chances of stellar collisions, forced mergers, or the rapid creation of tight, unstable binaries that will explode or spiral together later. The system we observe today, then, might not be the original. It could be a wounded, diminished remnant of a once even larger family. Some astronomers now look at the runaway stars speeding through the galaxy and wonder. When we trace their paths backwards, they don't always point to a single, obvious home. Perhaps their origin was not a stellar billiard shot from within a system, but a tidal stripping event where an entire stellar family was raided by a passing giant, its outermost members scattered like leaves in a galactic wind. Similarly, when we find a subsystem of 3 or 4 stars locked in orbits so tight they seem ready to shatter, we might be seeing the compressed, traumatized core of a system that survived a flyby. The galaxy is a busy place, and over billions of years, close encounters are inevitable. The decuple system we see today, with its precise count of 10, may simply be in a temporary state of calm, a lull between galactic storms, its current configuration a direct testament to the last time something immense and dark passed silently through its neighborhood. This galactic flyby catastrophe reveals a deeper truth about survival in chaos. Nature, it seems, builds these families not at random, but with a hidden architectural blueprint. Astronomers call it the hierarchy problem, and the solution is a principle of celestial organization. The most stable way to pack 10 stars into one gravitational cage is not as 10 individuals swirling in a free-for-all. Instead, the system organizes itself into a series of nested levels like a set of Russian dolls. At the very center, you often find the tightest bond, a pair of stars locked in a frantic, intimate dance. This is a binary, call it pair A. Very close by, another equally tight binary whirls, pair B. These two binaries don't just exist side by side, they themselves orbit a common center of gravity, forming a stable quadruple system. This quadruple core becomes the anchor. At a much greater distance, another group orbits this central mass. This could be a triple system, a tight trio of stars that has its own complex internal dance. That triple, as a unit, slowly circles the central quadruple. Now you have a septuple system, 7 stars bound in 2 distinct tiers. To reach a full decuple, you simply add another distant binary pair or a few single stars in wide, slow orbits around this already complex core. This hierarchical structure is not an accident, it is a requirement for long-term survival. It is the universe's method of dynamical packing. By organizing stars into tight, stable subgroups that are then widely separated from each other, the system minimizes the number of dangerously close encounters. The stars within a tight binary are so accustomed to each other's fierce pull that their dance is predictable. The quadruple core is a stable unit. The distant triple or binary interacts with that core as a single combined mass, not as four individual gravitational points. This drastically reduces the chaotic, random gravitational kicks that would otherwise quickly tear a disorganized swarm apart. We can see this blueprint in action by dissecting the architecture of AR Cassiopeiae, our first confirmed decuple. Its structure isn't 10 stars in a single messy ball. Observations strongly suggest a dense central quadruple system, likely two very close binaries orbiting each other. Around this, at several distinct distances, orbit additional binary pairs and single stars. It is a celestial empire with a powerful capital city and outlying provinces, each with its own local governance, all paying tribute to the central gravity. This nested order is the silent guardian. It is the reason these systems can persist for hundreds of millions of years. Without this hierarchical architecture, the relentless gravitational perturbations would have scattered the stars to the galactic winds in a cosmic blink of an eye. The stunning chaos of 10 suns is therefore built upon a foundation of exquisite hidden order. That hidden order depends on a gravitational glue we can barely see. Among the 10 brilliant suns, there may be dozens of failed stars silently holding the chaos together. These are brown dwarfs, substellar objects caught in a cosmic identity crisis. They form like stars from collapsing clouds of gas, but they never gather enough mass to cross the critical threshold, to ignite the sustained hydrogen fusion that makes a true star shine. They are cosmic embers, cooling and fading from a brief red glow into near invisibility, radiating only a faint whisper of infrared heat. In a decuple system, these dark orbs could be the unseen architects of stability. Their role is one of pure, silent gravity. Imagine a pair of stars in a tight binary orbit. There are 5 special points in space around them, called Lagrange points, where the gravitational pulls from the 2 stars and the centrifugal force of orbit perfectly balance. An object placed at one of these points, like the L4 or L5 points leading or trailing the binary in its orbit, can stay there almost indefinitely. A brown dwarf with substantial mass but no disruptive light or stellar wind could occupy such a point. It becomes a gravitational keystone, its mass helping to lock the geometry of that binary pair, making their dance more resistant to the tugs from the other 8 luminous stars. Alternatively, a swarm of brown dwarfs could circle the entire system's outskirts, a dark halo whose collective gravity gently shepherds the inner stellar members, preventing their orbits from drifting into dangerous, destabilizing paths. They add crucial mass, the very thing astronomers find missing in their calculations, without adding the violent radiation or magnetic fury that would tear the system apart. Detecting these shadowy anchors is one of astronomy's great technical challenges. Their faint infrared glow is drowned out by the blistering light of their stellar neighbors. Finding them requires either blocking that stellar light with a coronagraph in space-based telescopes, hoping to directly image a faint, cool dot nearby, or measuring with exquisite precision the astrometric wobble of the visible stars. If a brown dwarf is there, its gravity will cause the stars it orbits to make a tiny, cyclical shimmy in the sky, a telltale dance partner revealed only by its pull. Confirming a population of brown dwarfs in a decuple system would be a monumental discovery. It would finally solve the missing mass problem, completing the true census of this celestial family. More importantly, it would reveal that the stability of 10 suns does not rely on luminous stars alone, but on a hidden council of dark, silent guardians whose gravity writes the rules the light must follow. Those dark guardians provide a stable frame, but the stars themselves weave a far more energetic web. When multiple magnetically active stars share a crowded space, their invisible force fields do not simply coexist, they clash and connect. Each star is wrapped in a vast, teardrop-shaped bubble of magnetism called a magnetosphere, a zone where its magnetic field dominates the flow of charged particles. In a decuple system, during the close orbital passes of stellar pairs or subgroups, these colossal magnetic bubbles can be pushed together. The result is not a gentle merging, but a violent snap. Opposing magnetic field lines break and reconnect, forging new links in a process called magnetic reconnection. This event unleashes a torrent of energy, accelerating electrons and protons to nearly the speed of light. For a brief, furious window, a temporary magnetic highway opens between the two stars. Charged particles, once trapped around one sun, are now funneled at incredible velocities along these newly connected field lines, racing across the void to slam into the atmosphere of its neighbor. It is a stellar-scale electrical circuit suddenly completed across millions of kilometers. The implications are staggering. This could be the hidden trigger for system-wide fireworks. A superflare erupting on one magnetically furious red dwarf might, via this reconnection highway, inject a surge of particles directly into the magnetosphere of a companion star. That influx could destabilize the second star's own magnetic fields, triggering a sympathetic flare minutes or hours later. We would observe not random outbursts, but a cascade of eruptions, a chain reaction of stellar fury leaping from one sun to another like lightning between charged clouds. While this magnetic network has not yet been directly imaged, astronomers have a plan to listen for its roar. They train radio telescopes on these chaotic points of light, searching for a specific type of signal called non-thermal synchrotron emission. When those ultra-fast electrons spiral along curved magnetic field lines, they don't just travel, they scream. They emit a broad, hissing radio roar, a signature of intense, large-scale magnetic activity. Detecting this synchrotron radio buzz from a decuple system would be the smoking gun. It would tell us that the energy in that system isn't just contained within individual stars, but is flowing between them along vast, invisible conduits. We would be witnessing not just 10 separate weather systems, but a single, interconnected stellar climate, a tempest of particles and magnetism on a scale that dwarfs our entire solar system, where a storm on one sun can directly spark a hurricane on another. The magnetic storms between stars would shred any world that dared to orbit too close, yet the most resilient planets might find sanctuary at a staggering distance. While the concept of a planet orbiting a single star within a decuple system is daunting, there exists an even more precarious configuration, a world that doesn't circle one sun but dances around two at once. These are circumbinary planets, and their improbable existence is one of the greatest feats of gravitational engineering in the cosmos. In simpler systems like Kepler-47, some 3,000 light-years away, we have proof it can happen. There, a planet roughly the size of Neptune orbits a pair of stars, one sun-like and one a dim red dwarf, completing a year in about 300 Earth days. It is a world with two suns in its sky, a real-life Tatooine. But transplant this scenario into the heart of a decuple system, and the stability required becomes almost mythical. Here, a circumbinary planet would not just answer to the complex tug-of-war of its two host stars. It would also feel the persistent, rhythmic pull of 8 other massive bodies scattered throughout the system, each one a gravitational bully trying to disrupt its path. Survival in such an environment demands a very specific cosmic address. The planet must find a narrow band of space, a delicate stability zone far enough from its host binary to avoid being torn apart by their competing pulls, yet not so far that the gravity of the other stars can easily pluck it away. This zone is not a calm, circular track. It is a wobbly, precessing ring. The planet's orbit itself would slowly rotate like a hula hoop around the binary, its entire path turning over millennia due to the relentless gravitational nudges from its stellar neighbors. Its year would not be a simple ellipse but a complex rosette-shaped pattern traced in space, a constant negotiation between multiple competing forces. For such a world, the sky is a theater of perpetual motion. The two central suns would perform their own intimate dance, sometimes eclipsing each other, sometimes appearing close together as a brilliant double star. Further out, the other 8 stars would drift as brilliant wandering points of light, some moving in predictable arcs, others on slower, more chaotic paths. True darkness might be a rare event, occurring only when all the stars are fortuitously aligned on the other side of the planet. The temperature on this world would swing wildly, not with seasons, but with the ever-changing alignments of its many suns. A close pass from a bright, blue giant star could flood the planet with intense ultraviolet radiation, while a period dominated by the gentle light of distant red dwarfs might bring a deep, protracted chill. The gravitational tides from this celestial crowd would constantly knead the planet's interior, likely fueling global volcanic activity and keeping the crust in a state of permanent, trembling unrest. That a world could coalesce and persist in such a gravitational shooting gallery is a testament to the universe's capacity for fine-tuning. It suggests that within the apparent madness of 10 suns, there are still pockets of exquisite, if temporary, order, places where the chaos cancels itself out just enough for a speck of rock and metal to hold its place in the cosmic dance. The light we receive from these 10 suns is not just a blended point, it is a blended voice. When astronomers pass that chaotic starlight through a spectrograph, they don't get a clean, simple rainbow. Instead, they get a spectral soup, a dense, overlapping tangle of dark absorption lines from every single star in the system, all superimposed upon one another. Each star, depending on its temperature and composition, imprints its own unique pattern of lines onto the light. A hot, blue O-type star will show strong lines of ionized helium. A cooler, sun-like star will show prominent lines of neutral metals like iron and calcium. In a decuple system, all of these patterns are printed on top of each other in a single, nearly indecipherable mess. The monumental task of spectral disentanglement is to take that blended light and pull it apart, to assign each and every absorption line back to its original stellar source. It begins with a library of templates, the spectral fingerprints of every known type of star, from the hottest to the coolest. Astronomers use sophisticated computer algorithms to try thousands of different combinations of these templates, shifting them back and forth in wavelength to account for the Doppler effect. A star moving toward us has its entire spectral pattern shifted slightly toward the blue. A star moving away is shifted toward the red. The algorithm's job is to find the perfect combination of 10 different stellar templates, each shifted by a different amount that, when added together, perfectly recreate the chaotic soup they observed. It is an exercise in cosmic forensics, like listening to a choir of 10 singers all performing different songs at once, and trying to isolate each individual voice, identify the singer, and measure how fast they are moving toward or away from the microphone. When it succeeds, the payoff is immense. From that disentangled spectrum, scientists can read the temperature of each star, classifying it precisely. They can estimate its mass and evolutionary state. The depth and width of specific lines reveal surface gravity, telling them if a star is a bloated giant or a dense dwarf. Most crucially, they can measure the radial velocity, the speed of each star along our line of sight, with exquisite precision. By taking spectra over months and years, they can watch those radial velocities change, tracing out the complex orbital dances of each member. This process is only possible at the cutting edge of technology, requiring not just high-resolution spectrographs that can see the finest details in the light, but immense computational power to run the millions of calculations needed to find the solution. It is a frontier of modern astrophysical data analysis, where the most profound secrets of 10-star chaos are hidden not in the light itself, but in the nearly impossible task of untangling it. That spectral fingerprint is a snapshot of motion toward or away from us, but to prove a true family, we must see them move together across the sky. This is the proper motion tango, a celestial waltz observed over decades. Every star in the galaxy drifts sideways against the distant backdrop of faraway galaxies, a tiny, creeping motion called proper motion. For a group of 10 stars to be a true, bound decuple system, they must share this journey. They must all be traveling in the same direction at nearly the same speed, like a flock of birds flying in tight formation through the void. The proof comes from missions like the European Space Agency's Gaia Observatory, a celestial cartographer of unprecedented precision. Gaia does not just look at stars, it measures their positions, distances, and motions across the sky with an accuracy akin to spotting a coin on the moon from Earth. When its data is focused on a candidate decuple system, it reveals the definitive truth. All 10 points of light will show that same shared drift, their proper motion vectors pointing like parallel arrows across the galaxy. But within that unified march, Gaia detects something even more beautiful: tiny, rhythmic wiggles in each star's path. These are the orbital dances, the gravitational signatures of their complex relationships. As one star swings around its binary partner, it doesn't just orbit an empty point. It causes the center of mass of that pair to wobble ever so slightly in its skyward trek. That wobble is a direct measure of the unseen companion's gravitational influence. This precise astrometry allows astronomers to separate the true family from an imposter, an optical multiple. Sometimes, from our vantage point, two stars that are actually hundreds of light years apart can appear right next to each other in the sky, a simple trick of perspective. They share no gravitational bond, they are strangers passing in the galactic night. Gaia's proper motion data instantly exposes this illusion. In an optical pair, the two stars will have completely different proper motions, one drifting northwest while the other heads southeast, proving they are on independent journeys and merely aligned by chance from our viewpoint. The shared proper motion of a true decuple is the gold standard proof of a physical connection. It is the cosmic equivalent of a surname, the evidence that these 10 suns are not a random crowd, but a dynasty born from the same cloud, bound by gravity, and destined to travel the galaxy together for eons to come. This shared journey across the galaxy begins in a storm of invisible light. Before a decuple system settles into its long-term chaos, it spends its youth bathed in a searing, high-energy glow. Observatories like Chandra and XMM Newton, which see the universe in X-rays, reveal these young stellar families not as points of visible light, but as diffuse, blistering clouds of radiation. This is the X-ray signature of stellar infancy, and in a system of 10 suns, it is amplified to a terrifying intensity. The source is the stars themselves, particularly the pre-main sequence stars known as T-Tauri variables. These are stellar toddlers, still contracting under their own gravity and spinning at breakneck speeds. This rapid rotation, combined with their turbulent interiors, generates monstrous magnetic fields. These fields twist and snap above the star's surfaces, in regions called coronas, heating plasma to millions of degrees and unleashing a constant barrage of X-rays. In a solitary star, this is a phase of high activity. In a decuple nursery, it becomes a collective radiation bath. 10 young, magnetically furious stars are all doing this at once, their individual X-ray coronas merging into a single, system-wide fog of high-energy particles. This pervasive X-ray glow is more than just a symptom of youth. It is an active sculptor of the system's future. Any leftover material from the star's birth, the vast protoplanetary disks of gas and dust where planets could form, is exposed to this relentless barrage. The process is called photoevaporation. When an energetic X-ray photon strikes a molecule in the disk, it can blast it apart, heating the gas and giving it enough energy to escape the star's gravity entirely. Imagine a gentle mist being hit by a blowtorch, the droplets instantly turning to steam and vanishing. In a decuple system, that blowtorch is coming from 10 different directions. The combined X-ray flux can strip away the outer layers of these disks at an astonishing rate, truncating them and robbing them of the raw material needed to build gas giants. It creates a hostile environment where planet formation is a race against time. A fledgling world must coalesce from the dust and ice before the very disk that feeds it is boiled away by the collective fury of its stellar siblings. This paints the decuple nursery not as a serene cradle, but as a violent, energetic crucible. Stars are born not into solitude, but immediately into a crowded, social environment where their first act is to blast their neighbors with radiation, fundamentally altering each other's potential to build planetary families. The chaos of orbits begins here in these earliest moments, with a storm of X-rays that writes the rules for everything that follows. The X-ray fury of youth gives way to a slower, more insidious gravitational rhythm. Within the crowded architecture of a decuple system, a subtle orbital mechanism operates in perpetual overdrive, a phenomenon known as the quasi-Lidov mechanism. In its simplest form, it describes a gravitational conversation between three bodies. Imagine a tight binary pair and a third star orbiting them both at a much greater distance. If that outer star's orbit is tilted, its persistent gravitational tugs don't just pull, they twist. Over thousands of years, it trades orbital characteristics with the inner binary. The inner orbit's tilt, or inclination, is slowly pumped down, and that lost energy is transferred into making the orbit more and more elongated or eccentric. Then the process reverses, the eccentricity drains away, and the inclination pumps back up in a slow, cyclical exchange. Now amplify that simple conversation into a shouting match. In a decuple system, every star or tight subgroup is not influenced by just one outer perturber, but by 8 or 9 others, all pulling from different angles and distances. Each of these external stars imposes its own quasi-Lidov cycle, each with a different strength and rhythm. The result is a gravitational symphony of overlapping oscillations, a chaotic interference pattern where the effects can either cancel out or, more terrifyingly, reinforce each other. For any given star, its orbital path is never stable. It is constantly being sculpted by this chorus of distant voices. Its orbit will gradually stretch from a near circle into a needle-thin ellipse, a process that can take tens of thousands of years. The moment of greatest danger comes at periastron, the point of closest approach in that elongated orbit. A star on such a path spends most of its long year drifting lazily in the frozen outer reaches of its orbit. But then it plummets inward, accelerating to incredible speed as it screams through the inner system. At periastron, it passes breathtakingly close to the other stars at the core. In that moment, the gravitational tides become monstrous. If it passes near another single star, the two can be gravitationally scattered, one hurled onto an even wilder path or even ejected. If it sweeps past a tight binary, the intruder's gravity can violently perturb that delicate dance, shrinking the binary's orbit or triggering a merger. In the most direct catastrophe, the plunging star's path might intersect another's entirely, leading to a stellar collision of apocalyptic force. This mechanism is the silent, relentless engine driving the system's evolution. It explains why these families cannot be static. The quasi-Lidov cycles, supercharged by multiple perturbers, ensure that orbits are never frozen. They are living, breathing things that periodically drive stars into zones of extreme danger. A pair of stars that have coexisted peacefully for 1,000,000 years might suddenly have their orbits tuned into a destructive resonance by these cycles, leading to a merger that births a blue straggler. A seemingly stable planet hosting orbit around a single star could be utterly destroyed when the Kozyledov effect from a distant binary pumps its eccentricity to extremes, either flinging the world into its star or casting it into the void. It is a clockwork of chaos operating on timescales far beyond human history, yet dictating the ultimate fate of every member in this celestial cage. While the stars blaze with light and fury, it is this invisible gravitational calculus, this patient exchange of orbital energy, that truly writes the story of their lives and deaths. That gravitational clockwork of chaos leaves behind a silent, glowing graveyard. The most profound evidence of the violence within a decuple system is not found in the brilliant light of its 10 suns, but in the faint, warm afterglow that clings to them. Space telescopes like Spitzer and Herschel, designed to see the universe in infrared light, have trained their eyes on these chaotic points and discovered something extraordinary. Beyond the expected blaze of the stars, they detect an excess, a persistent, diffuse infrared hum, a signature of warmth that should not be there if only stars were present. This is the infrared excess, and it is the telltale fingerprint of dust, countless trillions of microscopic particles heated by the starlight to temperatures of a few hundred degrees. In a decuple system, this signal is not a simple, smooth halo. It is a complex, lumpy, and often warped structure, a map of celestial wreckage on a staggering scale. This is the system's debris disk, but calling it a disk is a generous simplification. It is more accurately a vast, chaotic cloud of pulverized rock and ice, the aftermath of a construction project that failed spectacularly or is still violently ongoing. Each mote of dust is a tombstone for a world that never was. The material represents the leftover building blocks of planet formation, the planetesimals that failed to coalesce into a stable planet. But in this gravitational shooting gallery, they are never left in peace. They are constantly colliding. When two mountain-sized planetesimals slam together at thousands of kilometers per hour, they don't just merge, they shatter. They are reduced to a fine, glittering powder that adds to the infrared glow. This means the dust we see is not a relic of the distant past. It is being actively manufactured right now by relentless bombardment. The system is a self-sustaining wrecking yard where the destruction of failed worlds feeds the cloud that proves their destruction. Yet, even as new dust is created, it faces immediate peril. The intense radiation pressure from 10 fierce stellar winds acts like a cosmic broom. Photons of light, though massless, carry momentum. When they strike a tiny dust grain, they give it a gentle but persistent push. For the smallest particles, this pressure is stronger than the pull of gravity. They are simply blown out of the system entirely, exiled on a one-way trip into interstellar space. Meanwhile, the gravitational perturbations from the stars constantly stir the disk, herding dust into clumps and rings, and flinging vast swaths of it into the central furnace or out into the dark. Studying the precise temperature and distribution of this dust is like reading a forensic report on the system's gravitational landscape. Warmer dust huddles closer to the stars, tracing the regions of most intense stellar heating. Gaps and sharp edges in the dust cloud often point directly to the orbit of a hidden substellar object, a planet or brown dwarf whose gravity has cleared a path like a cosmic snowplow. The very warping of the disk, its tilt and twist, is a frozen record of past close encounters, a gravitational memory written in microscopic stone. This faint infrared whisper, therefore, tells two simultaneous stories. It is a real-time chronicle of endless, violent collisions, a sign that the chaos of 10 suns permits no permanent peace, even for mountain-sized rocks. And it is an archaeological record, a preserved map of the gravitational forces that have shaped this stellar family for millions of years. The dust is both the product of the chaos and the most sensitive tracer of its invisible rules. The faint infrared whisper of colliding dust is a testament to forces that are almost impossible to predict. To truly understand how a family of 10 suns can survive its own chaos, we must turn to the most powerful supercomputers on Earth, running simulations of staggering complexity. This is the realm of the N-body problem, a mathematical challenge that has haunted astronomers for centuries. In its simplest form, it asks a deceptively easy question. Given a group of objects like stars or planets, all pulling on each other with gravity, can we predict where they will be in the future? For two bodies like Earth and the Sun, Isaac Newton gave us an elegant solution, a perfect elliptical orbit. Add a third body, however, and everything changes. There is no neat, closed-form equation that can perfectly describe their motions indefinitely. The system becomes chaotic, sensitive to the tiniest of changes. Now multiply that complexity by 10. An N-body simulation for a decuple system must account for every single gravitational interaction. Each of the 10 stars feels the pull of the other 9, and those pulls are constantly changing as the stars themselves move. It is a web of 45 unique gravitational relationships, all evolving in real time. To model this, scientists divide time into unimaginably small slices, mere fractions of an orbit. For each slice, the computer calculates the gravitational force on every star from all the others, updates their velocities and positions, and then takes the next tiny step forward. To simulate even 1,000,000 years of the system's life, which is a blink in cosmic terms, requires trillions upon trillions of these calculations. The demand for processing power is colossal, pushing the limits of the world's fastest supercomputers for weeks at a time. But the greatest challenge isn't just raw computation, it is the inherent chaos of the system itself. In any digital calculation, there are minuscule rounding errors. In a simple system, these errors are negligible. In a decuple simulation, they are catastrophic, because the gravitational forces are so exquisitely sensitive to position. A discrepancy smaller than the width of an atom in the initial setup can, over thousands of simulated orbits, blossom into a completely different future. One run might show a stable configuration lasting 1 billion years. An identical run with an imperceptibly different starting point might see two stars collide in only 10 million years. This is the essence of chaos theory, often called the butterfly effect, playing out on a stellar scale. It means these simulations cannot give us one definitive answer for how a specific system will evolve. Instead, they give us a range of probabilities. Scientists run the same simulation thousands of times with slightly randomized starting conditions, creating a statistical portrait of possible fates. What they find is humbling. The vast majority of random configurations of 10 stars are not stable. The gravitational tensions are simply too great. In most simulation runs, the system rapidly dismantles itself. Close encounters lead to slingshot ejections, hurling stars into the void. Other stars are driven into mergers, creating blue stragglers. Often, within a few 100 million simulated years, the decuple system has boiled down to a stable core of 6 or 7 stars, surrounded by a halo of escapees. This makes the handful of decuple systems we have actually observed in the cosmos profoundly special. They are not random arrangements, they are the rare survivors. Their very existence tells us they must have formed with a specific, stable architecture from the beginning, likely that hierarchical nested structure, and have somehow avoided the gravitational pitfalls that destroy most of their kind. These simulations are more than just forecasts, they are laboratories for cosmic history. By tweaking the initial conditions, scientists can test different theories of how these systems formed. Did they arise from a single collapsing cloud that fragmented into 10 pieces? Or were they built through a series of gravitational captures in a dense cluster? The simulations that produce long-lived systems matching the broad properties of real ones, like AR Cassiopeiae, point us toward the most likely birth stories. So when we look at those 10 points of light, we are not just seeing chaos. We are witnessing a cosmic lottery winner, a configuration so finely balanced it has, against all odds, endured. This relentless gravitational kneading has a direct physical consequence, a planetary fever that can melt worlds from the inside out. For any rocky planet or large moon orbiting a star in a decuple system, the tidal forces are not an occasional event, they are a constant, crushing reality. The gravity from the other 9 stars never stops pulling, creating a ceaseless flex in the very body of the world. Imagine squeezing a rubber ball in your hand over and over, never letting it rest. The friction from that constant deformation generates heat. On a planetary scale, this tidal heating is a furnace of unimaginable power, far surpassing the gentle, steady warmth from radioactive decay in Earth's core. We have a local example of this process in our own solar system. Jupiter's moon Io is the most volcanically active body we know, its surface a cracked, sulfur-stained canvas of erupting plumes and fresh lava flows. This hellish landscape is powered solely by tidal heating. As Io orbits Jupiter, the immense gravity of the giant planet, combined with the rhythmic tugs from the other Galilean moons, stretches and squeezes Io's interior like a ball of clay. That friction melts rock, creating vast underground seas of magma that constantly erupt to the surface. Now, amplify that scenario by an order of magnitude. In a decuple system, a rocky world would not answer to one giant planet and a few moons. It would be subject to the persistent, shifting pulls of 9 other massive stars, each a gravitational bully yanking it in a different direction. The tidal flexing would not be rhythmic and predictable but chaotic and extreme. The internal heat generated would be catastrophic. For a planet similar in size to Earth, the outcome would be apocalyptic. The crust, rather than being a stable shell, would become a fragile skin over a churning ocean of molten rock. The entire mantle could liquefy, turning the world into a global magma ocean, a sphere of incandescent fury with perhaps only a thin, temporary scum of solid rock forming on its surface before being subsumed again. Tectonic activity would not be the slow drift of continents, but a continuous global shattering. The surface would be a network of planet-spanning fissures, vomiting lava and superheated gas into an atmosphere choked with ash. It would be a world in the throes of a permanent, violent birth, its very substance being churned by the hands of 10 suns. Any hope for a stable surface for oceans or continents would be vaporized in this gravitational stress cooker. The planet would become a testament to pure geological torment, a glowing ember whose light is not reflected starlight, but the radiance of its own molten heart, kept boiling by the endless, distant dance of its stellar masters. The violent stellar nova that lit up ancient skies were not random acts of cosmic violence. For centuries, astronomers in China, Korea, and the Islamic world meticulously recorded the sudden appearance of guest stars, points of brilliant light where none had been seen before, which then faded over weeks or months. These were not new stars being born, but old stars dying in spectacular, repetitive fashion. Today, we understand these events as classical nova, and their most likely breeding grounds are the very environments we have been exploring, the crowded stellar nurseries that give rise to decuple systems. The mechanism is a perfect recipe for disaster. It requires a binary pair where one star has already died, collapsing into a white dwarf, an Earth-sized sphere of degenerate matter with the mass of a sun. Its companion, still a normal star, orbits close enough that its outer atmosphere gets pulled away by the white dwarf's fierce gravity. This stolen hydrogen flows across space, piling onto the white dwarf's searing hot surface. For a time, it simply accumulates, a layer of fresh fuel on a dormant stellar furnace. But as pressure and temperature at the base of this layer climb past a critical point, a runaway thermonuclear explosion ignites. The entire accumulated shell of hydrogen detonates in a flash of staggering energy, blasting material into space at thousands of kilometers per second and causing the binary to shine with the brilliance of hundreds of thousands of suns. This is a nova. Crucially, the white dwarf itself is not destroyed. It survives the blast and the cycle begins anew. More gas is siphoned from its companion, building up for the next explosion tens of thousands of years later. In the crowded, dynamic environment of a decuple system, such close binaries are not rare anomalies, they are an expected product. The constant gravitational nudges from 8 other stars can herd stellar remnants and living stars into these dangerously intimate partnerships. This means a decuple system could be a nova factory, with multiple such ticking time bombs in its ranks, each erupting on its own long and lonely schedule. The fascinating possibility now emerges that some of those ancient guest stars, recorded by court astronomers watching for celestial omens, were in fact nova erupting within these 10-star families. Imagine a scholar in 11th century Song Dynasty China noting a brilliant new star in a familiar constellation. He documents its position, its brightness, and how it slowly fades over 50 nights. His record survives in imperial archives for a millennium. Modern astronomers, armed with precise coordinates from those historical texts, now turn their telescopes to that same patch of sky. What they find is not a single, obvious remnant like the Crab Nebula from a supernova. Instead, they find a faint, complex point of light. Through spectroscopy and photometry, they unravel it, revealing not 1 or 2, but 8 or 9 or 10 stars in a tangled gravitational embrace. And within that knot, they identify the smoking gun, a faint blue-white star with the spectral signature of a white dwarf, and right beside it, the telltale signs of a companion star whose atmosphere is being actively stripped away. The connection clicks. That faint, chaotic system we see today is the very same one that 900 years ago hosted a cataclysmic eruption. The brilliant guest star was the white dwarf's nova outburst, a temporary flare that briefly outshone all its stellar siblings combined before fading back into obscurity. Making this link transforms dusty historical records into a precious scientific dataset. It provides a precise date for a specific cataclysmic event within that system. By knowing exactly when that nova occurred, astronomers can calculate the rate at which the white dwarf is accreting material from its partner. They can estimate the mass of the white dwarf and even begin to predict when the next eruption might occur, tens of thousands of years from now. It stitches together human history and cosmic evolution, proving that the chaotic hearts of these stellar families have been writing their violent stories across our night sky for longer than our written records have existed. We are only now learning how to read them. The violent flashes of nova are dramatic, but a far more subtle pulse beats within the hearts of these stellar families. Some stars don't just shine, they sing. Across the cosmos, certain stars like Delta Scuti and Gamma Doradus variables experience rhythmic pulsations, their outer layers expanding and contracting as if breathing in a slow cosmic rhythm. These are not random flickers, but resonant oscillations, literal starquakes that travel through the star's entire interior. The science of listening to these vibrations is called astroseismology, and in a decuple system, it becomes a symphony of unparalleled clarity. When you have not one, but several pulsating stars all bound within the same gravitational cage, you hold a master key to their deepest secrets. Each pulsation mode is a direct probe into the star's hidden architecture. The frequencies at which a star quakes depend on its internal density, temperature profile, and composition. It is like striking a bell. A large, low-density bell produces a deep, slow gong, while a small, dense bell rings with a high, quick chime. By meticulously measuring the specific frequencies of a pulsating star, astronomers can perform a kind of celestial ultrasound. They can map the boundary between its radiative core and convective outer layers, gauge the speed of sound waves traveling through its plasma, and even estimate its internal rotation. This data yields remarkably precise measurements of the star's mass, radius, and age, often with far greater accuracy than any other method. In a decuple system, this technique transforms from a solo performance into a grand comparative study. Imagine having 10 siblings and being able to give each one a detailed medical scan. By applying astroseismology to multiple pulsating members of the same family, scientists gain a powerful, independent check on their models. They can measure the mass of one star from its pulsations and then verify that mass by seeing how it gravitationally influences its binary partner. They can determine the precise age of several stars from their internal chemistry and pulsation patterns. This is where the story of the system's origin comes into sharp focus. If all 10 stars show nearly identical astroseismic ages and similar internal compositions, it is strong evidence they are coeval, born together from the same collapsing cloud. But if one or two stars have a significantly different internal clock or a distinct chemical heartbeat, it points to a history of capture. That star would be an adopted sibling, a wanderer gravitationally snatched by the system long after its own birth. This seismic data becomes the ground truth against which all other theories are tested. Computer simulations of the system's chaotic evolution can be fine-tuned until they produce stellar masses and ages that match the precise numbers derived from the starquakes. It allows astronomers to rewind the gravitational tape with newfound confidence, to understand which stars may have swapped partners, which ones have lost mass to a neighbor, and how the hierarchical architecture we see today emerged from the primordial chaos. The gentle, rhythmic pulsing of these stars, often drowned out by the glare of their brighter siblings, becomes the most reliable narrator of their shared history, a quiet conversation of vibrations that tells the true story of a family forged in fire and bound by gravity. The quiet vibrations of astroseismology reveal a star's personal history, but its chemical fingerprint speaks of a much grander galactic past. Every star carries within its light a record of the raw materials from which it was forged, a value known as metallicity. This isn't just about iron or gold, but the total abundance of every element heavier than helium. In the cosmic story, these metals were not present at the beginning. The universe started with only hydrogen, helium, and a trace of lithium. Every atom of carbon, oxygen, silicon, and iron had to be forged later, inside the furnaces of stars or in their violent deaths. When a star forms, it locks in the chemical composition of the cloud that birthed it. That composition is a timestamp. A star born from pristine, early universe gas will have very low metallicity. A star born more recently from gas already enriched by generations of prior supernova will have a higher metal content. This is where decuple systems become galactic archaeologists. These monstrous families of 10 suns are not built from modest amounts of material. They require an enormous, dense, and rich reservoir of gas to form all at once. Such colossal nurseries were far more common in the chaotic, crowded conditions of the early Milky Way over 10 billion years ago. Indeed, spectroscopic studies of several candidate decuple systems reveal a telling signature, a notably low metallicity. Their starlight shows weaker absorption lines from heavy elements compared to younger stars like our Sun. They are not just old, they are ancient relics, fossils from the galaxy's first great wave of star formation. Studying them is like cracking open a cosmic time capsule. Within their tangled orbits and diverse stellar types, we see a preserved snapshot of the Milky Way's infancy. They show us the kinds of stars the young galaxy could produce, the maximum size of stellar families it could bind together, and the initial chemical conditions from which all later generations would arise. Their very survival for over 10 billion years is itself a staggering marvel. They have witnessed the galaxy's entire history, from a formless disk to its majestic spiral arms, all while maintaining their chaotic gravitational dance through countless close calls and near disasters. By analyzing the different stars within a single ancient decuple system, astronomers gain a powerful comparative tool. They can see how stars of different masses, all born from the same primordial soup, have aged over the eons. A hot, massive star in the system might be nearing its end as a red giant, while a tiny red dwarf born at the same time has barely begun its multi-trillion-year life. This allows scientists to test and refine models of stellar evolution under conditions that no longer exist in the modern, metal-rich galaxy. The low metallicity of these systems also influences their internal physics. With fewer heavy elements to act as cooling agents in their original birth cloud, the gas may have collapsed differently, perhaps favoring the formation of more massive stars or tighter binaries. Their persistence tells us that the hierarchical architecture we see is not a later development, but a necessary blueprint for survival from day one. These 10 star families are more than just celestial curiosities. They are living museums, holding within their light the untold story of our galaxy's wild and elemental youth. Buried within the orbital mathematics of such a system, a supremely elegant arrangement might hide. The concept of a Trojan body comes from our own solar system, where swarms of asteroids share Jupiter's orbit, forever leading or trailing the giant planet by 60 degrees. These positions, known as Lagrange points, are gravitational sweet spots where the pull of the Sun and Jupiter perfectly balance an object's orbital motion. Now scale this idea up to a stellar level. Within the intricate hierarchy of a decuple system, a pair of stars locked in a tight binary could act as a single gravitational unit, a combined primary. Theorists propose that a third, lower mass star could occupy the stable Lagrange point of this binary pair, tracing the same path around the system's center, but always maintaining a fixed position 60 degrees ahead of or behind the dancing duo. This would be a Trojan star, a celestial companion riding in a gravitational eddy created by its more massive partners. In the relentless turbulence of 10 suns, such a configuration would be an island of profound stability. The Trojan star would be shielded from the worst of the gravitational perturbations. Its position is locked by the balanced forces of the binary it follows, making it far less susceptible to being nudged into a dangerous new orbit by the other 7 stars in the family. It becomes a passive traveler, a silent witness carried along in the wake of a more powerful gravitational engine. The search for such an arrangement is a hunt for perfection within pandemonium. Astronomers would look for a specific signature in the radial velocity data. As they track the motions of the stars, they would find 3 stars with nearly identical orbital periods around the system's core. 2 of them would show the telltale back and forth wobble of a close binary, their velocities constantly shifting as they orbit each other. The third star, however, would show a much smoother velocity curve, but its orbital period would match the binaries exactly. Its light would also be consistently Doppler shifted by a fixed amount relative to the binary's center of mass, indicating it is perpetually leading or trailing at that crucial 60-degree angle. Discovering a stellar Trojan would be a landmark confirmation of celestial mechanics operating at its most refined. It would prove that even in the most crowded stellar neighborhoods, gravity can carve out pockets of serene clockwork order. This configuration would also open a new chapter in architectural possibilities for high multiplicity systems. It suggests that stability isn't only achieved through wide separation or complex hierarchical nesting, but can also be achieved through precise gravitational resonance, where stars become synchronized passengers on a shared celestial highway. For any potential planets, the implications are dizzying. A world forming within the sphere of influence of a Trojan star would experience a bizarre but consistent sky. Its primary sun would be the Trojan star itself, but its horizon would always be dominated by the brilliant, close-set pair of its stellar guardians, forever hanging in a fixed position in the heavens, a permanent double sunset or sunrise that never changes its place in the sky. The cosmic clockwork here would be both simple and profound, a rare melody of order sung quietly against the roaring symphony of chaos. That gentle, rhythmic pulse of starquakes is sometimes drowned out by a frantic, crackling static. Deep within the blended starlight of a decuple system, Astronomers can sometimes detect a specific kind of chaos, a rapid, random flickering that operates on timescales of minutes or even seconds. This is not the predictable dimming of an eclipse or the steady beat of a pulsation. It is the live broadcast of matter in freefall, the photometric signature of cosmic cannibalism. The source is an accreting binary, a pair where one star has died, leaving behind a white dwarf or neutron star, and is now actively devouring its living companion. As gas from the donor star spills over its gravitational boundary, it doesn't fall smoothly. It forms a swirling, superheated disk around the dense remnant, a maelstrom of plasma known as an accretion disk. Within this disk, turbulence reigns. Clumps of material spiral inward at incredible speeds, colliding and heating to millions of degrees before finally plunging onto the surface of the dead star. Each of these chaotic events, each clump of gas meeting its doom, releases a tiny, sharp flash of light. From our distant vantage point, these countless micro-flashes blend together into a continuous, crackling flicker, like watching the frantic, popping static of a detuned television screen superimposed on a steady lamp. In the integrated glow of 10 suns, this signal is a needle in a haystack. It adds a layer of rapid, random noise on top of all the other, slower variations from eclipses and stellar pulsations. To find it, astronomers must engage in a form of high-speed stellar surveillance. They use telescopes capable of high-cadence photometry, taking a brightness measurement not every few hours but every few seconds for hours on end. They then analyze this torrent of data, searching for the telltale statistical fingerprint of flickering, a specific pattern of randomness in the light that betrays the presence of an accretion disk in turmoil. Successfully isolating this signal is a monumental forensic achievement. It does more than just confirm an exotic binary, it acts as a cosmic pointer. It tells the researchers precisely which of those 10 points of blended light is the culprit, which specific star in that crowded field is the vampiric heart of the system. That one pinpoint of light, when examined more closely, will resolve into 2 stars, one a normal sun and the other a faint, searingly hot ember greedily pulling its partner apart. This method reveals stellar remnants that would otherwise be completely invisible, lost in the overwhelming glare of their brighter, healthier siblings. It is a way of listening to the quietest, fastest whisper in a roaring room, a whisper that speaks of gravity's most intimate and destructive embrace. Even the most precise gravitational map has a fuzzy border. Determining exactly where a family of 10 suns ends and the lonely galactic void begins is not a simple task of drawing a line. Astronomers face a fundamental challenge defining the true boundary of the system itself. The central concept they use is the Hill sphere, named for the American astronomer George William Hill. Imagine the gravitational reach of the entire decuple system as a bubble in space. Within this bubble, the collective pull of the 10 stars dominates over the gentle, background tug of the entire Milky Way galaxy. The surface of that bubble is the Hill sphere, the limit of the system's true sphere of influence. Any object inside it is, for all practical purposes, a prisoner of that stellar family's gravity. Any object outside is a free agent orbiting the galactic center independently. The size of this sphere depends on the total mass of the system and its distance from the galactic center. For a massive decuple system, this bubble can be light years across, a vast territory. Yet, out at those extreme edges, the binding grip is tenuous. A star orbiting slowly in the system's distant outskirts lives a precarious existence. It is here that the galactic tide exerts its subtle power. Just as the moon's gravity creates tides on Earth, the Milky Way's overall gravitational field creates tides on the scale of star systems. This galactic tide constantly tugs at the outermost members, testing their allegiance. A close encounter with a passing molecular cloud or another star cluster can inject just enough energy to push a loosely bound star over the edge, beyond the Hill sphere's invisible wall. Once outside, it is no longer a member even if its path appears similar for a time. It becomes a coincidental traveler, a stellar neighbor sharing the same galactic zip code, but not the same gravitational family. To decide membership, astronomers don't just look at a star's current position. They perform a celestial background check. They measure its velocity relative to the system's core with exquisite care. A true member will have a velocity that is just below the local escape velocity, meaning it is gravitationally bound, even if its orbit takes 1 billion years to complete. A coincidental passerby will have a velocity that exceeds escape velocity, even if by a small margin. Its path, when projected forward through the galaxy, will slowly diverge from the true family's path. The data from the Gaia Observatory, which charts the motions of billions of stars, is crucial for this detective work. It provides the precise proper motion and radial velocity needed to calculate these trajectories. Yet, even with this data, ambiguity remains. Some stars hover right on the threshold. Their measured velocities have a margin of error that straddles the escape velocity line. Is it a distant, barely bound 10th member on a million-year orbit, or is it a recently captured interloper that will leave in another million years? This debate is not academic. It is the very first and often most contentious step in studying any high multiplicity system. Before you can understand the dynamics of 10 suns, you must agree on which 10 suns you are actually talking about. Different research groups using slightly different criteria or updated velocity measurements can publish conflicting catalogs. A system celebrated as a decuple in one paper might be listed as a nonuple in the next, its 10th star demoted to a mere background companion. This uncertainty forces humility. It reminds us that the cosmos rarely offers clean edges. The chaotic families we seek to define are not static islands, but dynamic entities with fuzzy, evaporating borders, constantly gaining and losing members in a slow, silent exchange with the galaxy itself. The formation of such a complex family demands a mechanism of spectacular efficiency. The leading theory points to a single, catastrophic event in a stellar nursery, a process called disk fragmentation. It begins not with 10 separate seeds, but with one. A vast cloud of gas and dust, perhaps hundreds of times the mass of our Sun, begins its inevitable collapse under gravity. As it spins, it flattens into a colossal protostellar disk, a swirling platter of material feeding a newborn star at its center. But if this disk is too massive, too cold, or rotates too slowly, it crosses a critical threshold. Its own self-gravity overwhelms the forces trying to hold it together. The disk does not smoothly feed the central star, it shatters. Like a pane of glass developing a web of cracks, the disk becomes gravitationally unstable. Spiral arms of denser gas emerge, and within those arms, knots of material begin to pull themselves apart from the whole. Each of these knots, if it contains enough mass and can cool efficiently, can collapse under its own weight. What was once a single feeding disk for one star suddenly becomes a crowded nursery for several. A binary or triple system is born from a single disk. This is not the end, but merely the first act. Each of these new stars can, in turn, form its own circumstellar disk. If conditions are right, those smaller disks can themselves become unstable and fragment again, creating a second generation of stellar seeds. You now have a hierarchical system growing from the inside out, a tight quadruple or quintuple system at the core, all originating from that single, overt protostellar disk. For a decuple system to emerge, the initial conditions must be perfect and extreme. The original cloud core must be staggeringly massive and rich in material, creating a primary disk of such enormous scale that its fragmentation isn't a one-time event but a cascade. It doesn't just break into 2 or 3 pieces, it shatters into a whole litter of stellar embryos, perhaps a dozen or more, all forming in rapid succession within the same orbital plane. This is in situ stellar multiplication, a single cloud giving birth to an entire stellar family in one frenzied burst of creation. The architecture we see today, with its nested binaries and hierarchies, is a frozen record of this sequential fragmentation. The tightest binaries are those that formed from the same unstable clump within the primary disk. Those binaries that orbit each other likely formed from sibling clumps that coalesced nearby. The entire system retains a memory of that initial disk, its orbital planes often showing vestiges of that shared birthplace, even after billions of years of gravitational stirring. This theory elegantly explains how 10 stars can share such a deep gravitational bond. They are not strangers captured over time. They are literal siblings born from the same swirling womb of gas, their complex relationships dictated by the chaotic but fruitful breakup of their colossal cradle. The relentless radiation from 10 suns creates an ultraviolet bath of unimaginable intensity. If even one of those stars is a searing hot O-type or B-type giant, its UV output alone can dwarf the total light of our entire sun. For any world orbiting within this stellar family, this is not merely a bright sky, it is an existential threat. The danger lies in the upper layers of a planet's atmosphere. When extreme ultraviolet photons slam into air molecules, they don't just warm them, they rip them apart, breaking bonds and ionizing atoms. This process deposits a tremendous amount of energy high above the planet's surface, heating the thin exosphere to staggering temperatures, tens of thousands of degrees. This superheated gas does not gently rise, it achieves escape velocity. The atmosphere doesn't just leak, it is violently blown off into space, streaming away from the planet in a continuous million-mile-per-hour wind. Astronomers call this hydrodynamic escape, and it operates with the devastating efficiency of a planetary sandblaster. Picture Earth's blue sky not as a gentle blanket, but as a fragile veil being relentlessly torn away by a stellar hurricane. The planet's lifeblood venting into the void as a glowing, comet-like tail pointing away from its dominant suns. Sophisticated computer models paint a grim portrait for terrestrial worlds in such an environment. Even a planet starting with a robust, Earth-like atmosphere of nitrogen and oxygen would not stand a chance. The combined ultraviolet flux from multiple hot stars would overwhelm the planet's gravitational grip. Calculations show that under such an assault, an Earth-mass planet could lose its entire primordial atmosphere in a cosmically brief span, perhaps only 10 to 100 million years. That is a geological eye blink, less than the time it took for single-celled life to emerge on our own world. The process is self-accelerating, a terrifying feedback loop. As the lighter elements like hydrogen and helium are stripped first, the atmosphere becomes enriched with heavier molecules, but even these are not safe. The intense UV breaks apart water vapor, releasing oxygen and hydrogen, and the lightweight hydrogen is immediately swept away. Carbon dioxide can be dissociated, with the carbon potentially forming a thin, hazy smog while the oxygen is lost to space or binds to the surface rocks. What remains is not an atmosphere, but a desiccated, tenuous shroud, or more likely, nothing at all. The planet is reduced to a barren, airless ball of rock, its surface directly exposed to the full fury of stellar radiation and micrometeorite impacts, its geologic history etched by cratering rather than erosion. The only conceivable defense against this atmospheric annihilation is a planetary magnetic field of extraordinary strength. Earth's magnetosphere acts as a shield, deflecting the charged particles of the solar wind and protecting our atmosphere from being sputtered away particle by particle. But the threat in a decuple system is different and far greater. It is not primarily the solar wind, but the direct photodissociation and heating by ultraviolet light. A magnetic field cannot stop a photon. Its role here would be more subtle and challenging. A powerful global magnetic field could help contain the atmosphere at the poles, potentially creating localized pockets of denser gas even as the equatorial regions are stripped bare. More importantly, it would protect the planet from the coronal mass ejections and stellar winds that would certainly accompany the UV fury. preventing those charged particles from adding their energy to the atmospheric escape process. For a world to keep its air, it would need a magnetic dynamo far more powerful than Earth's, likely driven by a rapidly spinning molten iron core kept churning by the intense tidal heating from its many stellar masters. It is a nearly impossible balancing act. The same tidal forces that could provide a protective magnetic field are also the ones that might melt the crust and vaporize any potential oceans. The ultraviolet bath thus imposes a brutal filter. It suggests that if life-bearing worlds exist in these systems at all, they are not Earth-like gardens under open skies. They are more likely to be subterranean or submarine worlds, where a global ocean is capped by a kilometers-thick shell of ice, or where life clings to existence in deep crustal aquifers, forever shielded from the scorching, sterilizing light of its 10 parent suns. The gravitational tides that strip atmospheres also bend the very fabric of space itself. When a decuple system drifts across our line of sight to a far more distant star, it doesn't just block the light, it warps it. This is the phenomenon of gravitational microlensing, a cosmic magnifying glass where the system's combined mass acts as a lens, briefly brightening the background star's light. But with 10 separate masses in chaotic motion, this is no ordinary lens. It becomes a fractured, kaleidoscopic prism, creating a light curve of impossible complexity. Instead of a single, smooth peak in brightness, the distant star's light would flicker and spike in a frantic, jagged pattern. Each star within the decuple system contributes its own tiny, moving warp in spacetime. As these individual warps sweep across the distant source, they create microcaustics, sudden, needle-sharp spikes of magnification. Imagine trying to read a book through a handful of moving, swirling magnifying glasses held over a candle flame. The light wouldn't just get brighter, it would dance and flare in a chaotic, unpredictable strobe. One moment, a tight binary pair might align perfectly with the background source, creating a paired double spike. The next, a single star on the far side of the system might pass by, adding a smaller, isolated bump. The resulting data would look less like a scientific graph and more like the seismograph of a planetary earthquake. This theoretical light curve is a direct mathematical portrait of the system's invisible architecture. The timing, height, and shape of each microspike encode precise information about the mass and position of the lensing object that created it. A broad, symmetrical spike might betray a single, isolated star. A sharp, asymmetric double peak would be the signature of a tight binary. A complex series of overlapping spikes could map the intricate dance of the central quadruple system. Most tantalizingly, a faint, unexpected microcaustic that doesn't correspond to any known visible star would be the ghostly fingerprint of a hidden mass, a dark brown dwarf, a rogue planet, or even that theorized central black hole. While such a perfectly aligned event has yet to be caught, the hunt is a profound exercise in patience and probability. Surveys like the optical gravitational lensing experiment monitor hundreds of millions of stars waiting for these chance alignments. To witness a decuple microlensing event would be to watch gravity itself draw a real-time map. It would offer a census of mass completely independent of starlight, revealing the dark members of the family that have eluded every other technique. It turns the entire chaotic system into a natural instrument, one that uses the warped space between its stars to illuminate its own deepest secrets. Locked in a permanent, one-sided stare, a star in this family endures a unique cosmic torment. This is the curse of synchronous rotation, a state forced upon it by the relentless tidal pull of its closest binary partner. Just as our moon forever shows Earth only one face, this star is tidally locked. One hemisphere, the day side, is perpetually bathed in the searing, up-close glare of its companion sun. The other hemisphere, the night side, faces eternally outward, turned away from that intimate partner. But here, in the decuple system, the curse takes a far more twisted form. That outward-facing night side is not looking into peaceful, empty space. It is staring directly into the gravitational storm. While one face is locked in a burning, static embrace, the other is witness to the chaotic ballet of the other 8 stars, their light waxing and waning as they whirl on their wild path. The temperature difference between these two hemispheres is not merely extreme, it is catastrophic. The day side, under constant, focused stellar fury, is baked to a temperature of thousands of degrees. The night side, receiving only the scattered, shifting light of the distant stellar crowd, exists in a deep, frigid freeze. This isn't just a hot pole and a cold pole. It is a star split into 2 different climatic worlds, seared and frozen simultaneously. This brutal divide warps the star's very nature. On a normal, spinning star, heat is distributed by rotation, creating a somewhat even global temperature. Here, that mechanism is broken. The star's atmosphere becomes a battleground for supersonic weather. Superheated gas from the dayside screams toward the night side in planet-sized hurricanes of plasma, only to cool, condense, and come crashing back in a relentless, global convection cycle of stellar proportions. This constant, lopsided churning does something profound to the star's magnetic field. Magnetic fields are generated by the motion of conductive plasma inside a star, its dynamo. The violent, asymmetric flow between the blazing day side and the frozen night side twists that dynamo into a configuration never seen in solitary stars. It could amplify the field to monstrous strengths, turning the star into a super flare factory, its magnetic loops snapping with pent-up energy from its distorted interior. Or it could create a bizarre, lopsided magnetic field, with one magnetic pole anchored on the day side and the other wandering weakly across the tortured night side. For any potential planet orbiting this tormented sun, the sky tells a story of cosmic schizophrenia. On the day side of the planet, if it too is tidally locked to the same star, the primary sun would be a permanent, unmoving fixture of hellish brilliance. But look to the opposite horizon, and you would see not darkness, but a shifting, multicolored tapestry. The other 8 stars would rise and set in a slow, complex dance, some brilliant and blue, others dim and red, their motions dictated by orbits that have nothing to do with your world's rotation. You would live on a terminator line between 2 universes, one defined by a single, relentless fire, the other by a silent, crowded galaxy of wandering suns, all bound together in a gravitational spell that grants no peace, only a perpetual, strained and silent scream. The ultimate stellar embrace is a shared coffin of plasma. This is the common envelope phase, a brief and violent chapter in the life of a binary star, and within a decuple system, it becomes a spectacle of forced intimacy. It begins when one star, often a red giant, exhausts its core fuel and swells to monstrous proportions. In a simple binary, it might gently transfer mass to its partner. But if the companion is too far away or the giant expands too quickly, something far more dramatic happens. The giant's outer atmosphere doesn't just flow toward its partner, it completely engulfs it. Both stars, the swollen giant's dense core and its smaller companion, are now orbiting inside a single, bloated shroud of hydrogen, a common envelope. They are no longer 2 dancers in a hall, but 2 people trapped inside a single, inflating balloon. Inside this thick, turbulent plasma, physics turns brutal. The companion star plows through this dense fog, and the drag is catastrophic. It robs the pair of orbital energy, causing them to spiral inward at a terrifying rate. Over a period that might be only months or years, their orbits shrink from a distance of perhaps 1 astronomical unit down to a mere fraction of that. All that lost orbital energy doesn't just vanish. It gets dumped into the envelope itself, heating it from within like a microwave. Eventually, the energy input is so immense that the entire vast envelope is blasted away, ejected into space as a beautiful, expanding nebula. What remains is the stripped-down, naked core of the giant, now a hot helium-burning star or a white dwarf, and its companion now locked in an incredibly tight, searingly hot orbit. They have survived a stellar burial and re-emerged with a bond forged in a stellar furnace. In the crowded decuple system, this intimate catastrophe might not be a natural evolution. It could be a forced marriage. A gravitational nudge from a passing third star could perturb a wide binary, sending one member diving into the expanded atmosphere of another, triggering the common envelope phase prematurely. It's a dynamical shove into a shared grave. The aftermath leaves behind two possible relics, each a smoking gun for this violent history. The first is a post-common envelope binary. You would find a tiny, incredibly hot white dwarf whirling around a main sequence star in an orbit so tight the entire year lasts only hours. Their spectra would be a study in extremes, the fierce, featureless ultraviolet continuum of the white dwarf superimposed on the more normal, lined spectrum of its living partner, both showing the rapid Doppler shifts of their frantic dance. The second outcome is a merger. If the companion spirals too deep before the envelope is ejected, it can plunge directly into the core of the giant. The two stellar cores coalesce, mixing their gases in a final, fiery embrace. The result is a single, rejuvenated star, often a blue straggler shining with a borrowed, violent youth, its outer layers enriched with the chemical ashes of its partner's demise. Finding either of these objects within the tangled light of a decuple system is like finding a spent cartridge at a crime scene. It is direct, forensic evidence that this specific family of 10 suns has witnessed one of the most extreme transformations a star can undergo. That tight binary of a white dwarf and a sun-like star ticking away like a stopwatch in the chaos is a permanent monument. It tells us that here, in this precise spot, a star died not in solitude, but in the act of consuming its neighbor, and the gravity of 8 other suns stood witness, holding the scene together long after the expanding nebula faded into the darkness between the stars. That shared stellar coffin leaves a gravitational fingerprint so subtle it can hide an entire world. Amidst the colossal tugs of 9 other suns, the gentle pull of a planet is like a whisper in a hurricane. Yet the whisper is there, a tiny, rhythmic shimmy in a star's path called the astrometric wobble. This is the telltale dance a star makes when an orbiting planet tugs on it. The star doesn't orbit the planet, of course, but both bodies orbit a common center of gravity, a point called the barycenter. For a star like our Sun pulled by a Jupiter, that barycenter lies just outside the Sun's surface, causing the Sun to trace a small circle in space every 12 years. In a quiet solar system, this wobble is detectable with precise instruments. But in a decuple system, the challenge is not just finding the whisper, it's identifying it within a cacophony of shouts. Every star in that family is itself wobbling madly due to the gravitational pulls of its 9 stellar siblings. Their paths are not smooth arcs but complex, processing loops within loops. The data stream from an observatory like Gaia isn't a clean line. It's a frenetic scribble of 10 overlapping, chaotic dances. Isolating a planetary signal requires a feat of computational exorcism. Astronomers must first build a perfect gravitational model of the entire 10-star system. They use every scrap of data radial velocities, eclipse timings, proper motions, to chart the precise orbits and masses of every single star. This model predicts exactly how each star should wobble due to the others. Only then can they subtract that predicted stellar chaos from the actual observed data. What remains in the residuals, the leftover noise, might contain the prize. They would search for a pattern in that noise, a tiny, periodic jitter superimposed on a single star's already complex path. The signature would be minuscule, a back-and-forth shift in the star's position on the sky measured in micro-arcseconds, a fraction of the width of a human hair seen from a mile away. And it would have to be strictly periodic, repeating with clockwork regularity over years or decades, the orbital period of the hidden world. The planet causing this wobble would almost certainly be a giant, many times the mass of Jupiter. Only such a behemoth could produce a gravitational nudge strong enough to rise even slightly above the leftover noise after the stellar motions are removed. Imagine the implications of success. Finding that signal would do more than add another exoplanet to the catalogue. It would be a monumental testament to planetary resilience. It would prove that a world can coalesce from the debris, cling to a stable orbit, and survive for billions of years in a gravitational environment where 10 stars are constantly trying to pull it away from its parent sun. That planet would be the ultimate survivor, a gravitational tightrope walker of cosmic proportions. Its existence would force us to rewrite the rules on where planets can form and how durable they can be. It would suggest that even in the most violent stellar neighborhoods, nature can still find a way to build and keep a world, a silent, massive sentinel orbiting a star that itself is dancing to the tune of 9 other suns. The silent gravitational whispers of a hidden planet would be drowned out by a scream of pure energy. Within the tangled heart of a decuple system, a different kind of survivor might announce its presence not with a wobble but with a roar. If one of those 10 suns is actually a stellar corpse, a neutron star or black hole, and it is actively feeding on a close companion, the system could host a microquasar. This is a scaled-down version of the monstrous quasars that blaze at the centers of galaxies, a tiny engine of terrifying power. Here, the dead star's gravity rips gas from its living partner, funneling it into a superheated accretion disk. But not all that material falls in. Some of it gets channeled by intense magnetic fields and launched away from the poles at nearly the speed of light, forming twin jets of plasma that punch out into space for light years. These jets are lighthouses of the radio spectrum. As the ultra-fast electrons within them spiral around magnetic field lines, they emit a distinctive hissing radio roar called synchrotron radiation. To our eyes, the system might look like a chaotic blend of 10 points of light, but to a radio telescope like the Very Large Array, a vast network of dishes in New Mexico, that same point could resolve into something spectacular. 2 long, thin, and brilliantly radio-loud beams shooting out in opposite directions. This is the signature of a microquasar, a cosmic blowtorch hidden in plain sight. Yet, in a decuple system, these jets would not fly straight. They would tell a story of constant gravitational assault. The relentless pulls from the other 8 stars would act like invisible hands, constantly pushing and twisting the base of the jets. Imagine trying to hold a garden hose steady while several people jostle your arms from different directions. The stream of water wouldn't be a straight line. It would whip and curve erratically. The radio jets would do the same on a stellar scale. They would be bent into graceful arcs or corkscrew shapes, their orientation slowly precessing or wobbling over time as the compact object's orbit is perturbed. The resulting radio structure would be a unique, dynamically sculpted masterpiece, a frozen snapshot of the gravitational forces at play at this very moment. Detecting this warped radio signature would be a monumental discovery. It would do more than just confirm the presence of a stellar mass black hole or neutron star. It would turn that object into a scientific probe. By meticulously mapping the bends and kinks in the jets, astronomers could literally trace the ambient gravitational field. Each curve encodes information about the strength and direction of the tugs from specific stellar neighbors. It would be like reading a weather vane in a hurricane, where the shape of the vane itself reveals the precise pattern of the winds that shaped it. This twisted radio scream, therefore, becomes a direct line into the invisible architecture of the chaos, a luminous map drawn by gravity itself. That twisted radio scream from a microquasar is a cosmic broadcast, but the stars themselves hold a quieter, more personal record of their past. Every star in a decuple system carries within its light a chemical fingerprint, a unique blend of elements forged in the galactic furnace. When astronomers point their most powerful spectrographs at these chaotic points of light, They are not just measuring brightness, they are performing a stellar blood test. This technique is called chemical tagging, and it seeks to answer the most fundamental question about this family of 10 suns. Are they truly siblings? The process begins by isolating the light of each individual star, a monumental task of spectral disentanglement we've discussed. Once separated, the high-resolution spectrum of a single star reveals not just broad categories, but precise abundances for dozens of specific elements: lithium, iron, carbon, oxygen, europium, barium. These elements were not present in the primordial cloud. They were forged inside earlier generations of stars and scattered into the galaxy by supernova and stellar winds. When a new star forms, it inherits the exact chemical mix of the cloud that birthed it. Think of it like a family recipe passed down through generations. Two stars born from the same giant molecular cloud at the same time will have absorbed the same ingredients. Their chemical fingerprints should be nearly identical, matching in the proportions of dozens of elements to a remarkable degree of precision. For a candidate decuple system, chemical tagging becomes the ultimate paternity test. By measuring the spectra of all 10 members, astronomers can look for that perfect familial match. If all 10 stars show the same distinct pattern, the same elevated levels of certain rare Earth elements or the same depletion of others, it is powerful, nearly irrefutable evidence that they are true siblings, born together from the same colossal womb of gas and dust. This chemical kinship would lock in their shared origin story, proving they are not a random assemblage of strangers captured over time, but a litter of stellar twins, quadruplets, and more, all sharing the same cosmic DNA. But the universe is rarely so neat. More often, the data reveals an outlier. Among the 9 matching chemical signatures, a 10th star shows a clear and significant deviation. Its spectrum might reveal a 20% higher abundance of barium, or a distinct lack of the element yttrium compared to its supposed siblings. This star is an imposter, or more accurately, an adopted child. It is a captured interloper, a star born in a different part of the galaxy, from a cloud with a different chemical history. Billions of years ago, this wanderer had a close encounter with the then younger 9-star system. The complex gravitational dance of that meeting resulted in a capture, the stranger being bound into the family, while perhaps one of the original members was flung out in exchange, a cosmic swap-meet transaction. This single chemical anomaly adds a profound new layer to the system's biography. It is not a static family portrait, but a dynamic history book. That outlier star is a permanent immigrant, its light telling the story of a long-ago merger between 2 distinct stellar families. By analyzing the precise differences in its chemical fingerprint, astronomers can even make educated guesses about the environment where it originally formed. Was it from a region richer in supernova debris? Did it form in a part of the galaxy with a different overall metallicity? This one star becomes a tracer, a piece of galactic history now permanently woven into the chaotic fabric of the decuple system. It proves that these families are not closed islands, but open gravitational ecosystems, capable of absorbing new members and losing old ones. Their 10-star count a temporary snapshot in an eons-long story of gravitational exchange. The stellar clock is always ticking, and in a family of 10 suns, the alarm is set to go off multiple times. The most massive members, those that burn brightest and fastest, are the first to reach their end. After billions of years fusing hydrogen in their cores, they exhaust that fuel. This marks the end of the main sequence, the stable, adult phase of a star's life, and the beginning of a volatile and spectacular demise. The core, now a shrinking ball of helium, begins to fuse heavier elements while the star's outer layers, no longer supported by the same outward pressure, swell to monstrous proportions. A star like our Sun will become a red giant, expanding to engulf the orbit of Earth. But in a decuple system, many of the stars are far more massive. They don't just become red giants, they become supergiants, inflating to sizes that could swallow the entire inner solar system. This transformation is not a gentle expansion into empty space. It is an aggressive territorial takeover within a densely packed stellar neighborhood. Imagine a single house in a crowded city block suddenly swelling to 1,000 times its size, its walls pushing into the homes on all sides. That is the reality for the companions of a dying star in this gravitational maze. The immediate threat is engulfment. A star in a tight binary pair will find its swollen sibling's atmosphere rushing outward to meet it. The companion doesn't just orbit a star anymore, it plows through the tenuous outer layers of a giant, a process that creates immense drag. This drag saps orbital energy, causing the two stars to spiral inward in a deadly embrace, often leading to a common envelope phase or a complete merger. But even if direct engulfment is avoided, the gravitational landscape is irrevocably altered. As the giant star bloats, its mass distribution changes. Material in its outer layers is held by a much weaker gravitational grip. This makes it susceptible to theft. A nearby companion star, or even a more distant one during a close pass, can exert tidal forces strong enough to pull great streamers of gas away from the giant, stripping its outer layers in a process called Roche-Lobe overflow. The dying star loses a significant portion of its mass to its neighbors, a stellar donation that changes everything. In gravity's ledger, mass is authority. For millions of years, the system's delicate dance was choreographed around the specific masses of its 10 members. When one star suddenly loses 20 or 30% of its substance, that gravitational authority vanishes. It is like removing the heaviest dancer from a complex group routine. The balance is shattered. The star's gravitational pull on its 8 siblings weakens. Their orbits, once finely tuned, are now miscalculated. Paths that were stable become chaotic. Orbits stretch into dangerous ellipses that bring stars into previously forbidden zones. A binary pair, its orbit tightened by the new dynamics, might be driven to merge. A distant, loosely bound star might find its tether so weakened that the next gravitational nudge from a neighbor sends it flying out of the system forever. This is the post-main sequence time bomb. The death of one star is not an isolated event, it is the pulling of a gravitational pin. The explosion is not in light but in motion. The system experiences a delayed chain reaction of instability, a dynamical rewiring that can take thousands of years to fully play out. A family that held together for 1 billion years can be unbound in a cosmic instant, not by a cataclysm, but by a slow sigh, the final breath of a giant that irrevocably changes the math of its entire world. The most profound chaos in a decuple system may not come from its birth, but from its first death, a single stellar senescence that sentences its 9 siblings to a future of scattering and silence. The light from a decuple system can play cruel tricks on the observer. Among the 10 points of blended brilliance, one might simply wink out of existence for years, even decades. This is the vanishing star illusion, a cosmic sleight of hand born from the system's relentless orbital clockwork. Imagine a faint red dwarf, a dim ember compared to its blazing blue giant sibling. If their orbits are aligned just right from our viewpoint, that faint star could spend a significant portion of its long orbit passing directly behind its brilliant companion. For a period that might last a human lifetime, the dwarf's feeble light is completely drowned out, swallowed by the glare of its neighbor. To our telescopes, it vanishes. The system's combined brightness dips slightly during the eclipse, but the spectral fingerprint of that specific star, its unique pattern of absorption lines, disappears entirely from the blended light. The system's stellar census drops from 10 to 9. An astronomer studying it today would swear the family has only 9 members, unaware that a 10th is merely in hiding. The illusion grows more profound with pulsating variable stars, particularly a class known as Mera variables. These are ancient, unstable red giants that breathe with a slow, cosmic rhythm, their brightness swelling and fading over periods of many months. At its peak, a Mera star in a decuple system might shine brightly enough to contribute a clear signature to the spectrum. But at its minimum, it can fade by a factor of 1,000, becoming virtually invisible against the backdrop of its stellar siblings. If an astronomer's data happens to be collected during that multi-year faint phase, the star will not appear in their catalogue. It has, for all observational purposes, vanished from the record. This creates a baffling historical discrepancy. Astronomers might pull century-old photographic plates from an observatory archive, plates that show the system's overall brightness was slightly different. Or they might find a spectral analysis from the 1970s that clearly lists 10 distinct sets of absorption lines, while their modern analysis finds only 9. The immediate, dramatic conclusion is that a cataclysmic event occurred. A stellar ejection, a violent merger, something must have permanently altered the family structure in the last 50 years. This launches a celestial detective story of the highest order. Is the star truly gone, or is it merely hiding? The detective's tools are patience and precise long-term monitoring. The first clue is in the timing. If the missing star is simply being eclipsed, its disappearance and reappearance should be periodic. Astronomers would scour decades of historical brightness data, looking for a repeating pattern of very subtle dips that correspond to the suspected orbital period. They would also hunt for indirect gravitational evidence. Even if the star is invisible, its mass still exerts a pull. Does the visible binary it orbits show a slight, unexplained wobble in its motion? Does the timing of other eclipses in the system show minute delays or advances, as if an unseen mass is gently tugging on the celestial clockwork? Finding these subtle gravitational whispers would be the smoking gun, proving the star is still there, just currently veiled. Without this long-term perspective, we risk a profound misreading of cosmic history. We might catalogue a system as a stable nonuple, a family of 9, when it is actually a decuple in a temporary state of concealment. We could mistakenly attribute the change to a recent, dramatic ejection event, rewriting the system's narrative based on a simple trick of light and alignment. The lesson is humbling. In these families of 10 suns, where orbits span centuries and stellar lives pulse over eons, a human lifetime is but a single, fleeting snapshot. What we see tonight is not the permanent truth, only a single frame in a movie that has been playing for billions of years. To understand the real architecture, we must watch and wait and learn to distinguish a permanent farewell from a star simply stepping behind the curtain for a very long intermission. Our view of a decuple system is a snapshot, a portrait of a family in motion. But that motion does not stop at the edges of the family itself. The entire system, all 10 suns bound together, is on a grand, sweeping journey around the heart of the Milky Way. This galactic orbit is not a serene cruise. It is a passage through a landscape of immense and varied gravitational forces, a journey that has actively sculpted the family we see today. Every 250 million years or so, the system completes one full circuit around the galactic center, a cosmic year that has repeated dozens of times since its birth. This orbit is not a perfect circle. It is likely elliptical, carrying the system on a long, looping path that takes it from the crowded, star-rich disk up through the sparse stellar halo, and sometimes even diving perilously close to the dense, chaotic bulge surrounding the supermassive black hole at the galaxy's core. Each of these environments presents a different kind of gravitational weather. The most dramatic events are tidal shocks. Picture the system sailing through a giant molecular cloud, a dark, frigid nebula containing the mass of 100,000 suns. As the decuple family passes by, the side of the system closest to the cloud feels a stronger gravitational pull than the side farther away. This difference, this tidal force, stretches the entire structure. It is a silent, system-wide strain. For the stars in the tightly bound inner core, this external tug is a minor nuisance, a passing tremor they can withstand. But for the outermost members, those already on wide, slow orbits at the very fringe of the family's gravitational grip, this shock can be the final straw. The extra energy injected by the tidal pull is enough to exceed their delicate binding energy. They are not ejected by an internal slingshot, but gently pried loose by an external hand. In a single, silent event, these distant stars drift away, their connection to the family severed forever. They become free agents, joining the vast population of field stars drifting through the galactic disk. Sophisticated computer simulations of this process paint a humbling picture. They suggest that the magnificent decuple system we observe today, with its precise count of 10, may not be the original structure at all. It could be the hardened, resilient core of what was once a much grander stellar association, perhaps a loose cluster of 50 or even 100 stars all born together in that fertile, long-ago nursery. Over billions of years, as this proto-cluster orbited the galaxy, it passed through dense spiral arms, skirted giant molecular clouds, and felt the intense tides near the galactic bulge. With each passage, it lost a few more of its most weakly bound members, a slow process of gravitational erosion. The current decuple system is the end product of this cosmic whittling. It is the dense nugget that remains after the softer, outer material has been stripped away by the relentless sandpaper of the galaxy itself. This transforms our understanding. We are not looking at a freakish, isolated family of 10. We are looking at a survivor, the final, tenacious kernel of a once great stellar dynasty, a testament to the fact that in the Milky Way, only the most tightly bound gravitational alliances can endure the long voyage through space and time. But survival in that galactic tide is not just a physical challenge, it is a philosophical one. For the ultimate inhabitants of a decuple world, the very sky would teach a different kind of physics and perhaps a different kind of wonder. This leads us to a purely speculative but utterly fascinating thought experiment. If an advanced civilization were to arise on a planet orbiting one of these 10 suns, how would they perceive the universe? Their entire framework of reality would be forged in a crucible of celestial chaos. Their astronomy would be a science of staggering complexity from the very beginning. Our ancestors looked up and saw orderly constellations, predictable planets, and a single sun marking the days and years. For them, the night sky would be a riot of moving lights. Simply determining what was a planet versus a distant star would be a monumental task, as their own suns would wander among the fixed background in dizzying patterns. Their calendar would not be a simple matter of one star's orbit. It would be a multi-layered calculation, a grand celestial clock with 10 interlocking hands. Significant dates might be marked by rare alignments, like the time when 3 of their suns converged in a brilliant triangle of light, or when their primary star was eclipsed by a close binary partner for the first time in a generation. Their mathematics would likely develop to handle complex orbital resonances and gravitational perturbations long before they ever conceived of a theory of relativity. The constant, violent stellar activity would not just be a scientific fact, it would be the central driver of their biology and culture. The surface, bombarded by unpredictable superflares and shifting radiation, would be a lethal place. Such a civilization would almost certainly be driven underground or into vast, shielded arcologies. Their entire concept of outside might be synonymous with danger, a place to be visited only with sophisticated protective technology. They might develop a profound reverence for geology and the deep, stable crust that protects them, while viewing the sky with a mixture of awe and terror. Would they see the chaotic dance of their 10 suns as a thing of terrible beauty, or as a constant, oppressive reminder of cosmic indifference? Their art and mythology would be unlike anything we can imagine. Instead of a single sun god, they might worship a pantheon of warring stellar deities. their myths explaining eclipses as battles and superflares as divine wrath. The concept of a quiet, dark night might be a mythical paradise, a lost golden age they could only dream of. This thought experiment does more than fuel science fiction, though it certainly makes for a compelling setting. It highlights a profound truth about intelligence in the cosmos. Environment shapes perspective in the most fundamental ways. A mind that evolved under 10 suns would process reality through a lens so alien to our own that communication might be nearly impossible. Their very sense of time, space, and stability would be different. When we search the skies for signs of extraterrestrial intelligence, we often listen for orderly, mathematical signals, patterns that suggest a mind like our own. But what if the most advanced message from such a world is not a neat prime number sequence, but a chaotic, pulsating signal that mirrors the complex orbital resonances of their home? It forces us to expand our imagination. The search for life cannot just be about finding Earth-like planets in calm solar systems. We must also consider that intelligence, against all odds, might have taken root in the most turbulent of cradles, and if it has, its view of the cosmos would be as magnificently strange and complex as the 10-star sky that shaped it. Billions of years from now, the last of the 10 suns will finally burn out. The brilliant, chaotic light show will have long since faded into cold, dark embers. White dwarfs will cool into black diamonds. Neutron stars will spin down into silence. Any central black holes will have consumed the last wisps of surrounding gas. The decuple system, once a riot of color and motion, will become a graveyard of ultra-dense shadows drifting in the void. Yet, in this ultimate darkness, the story is not over. It is merely entering its final, silent chapter, written not in light but in the ripples of space-time itself. Gravity never sleeps. The intricate gravitational bonds that held the family together for eons will now become the engine of its final destruction. The compact remnants, those white dwarfs, neutron stars, and black holes, are still there, still orbiting each other in the pitch black, but they are no longer moving through empty space. They are plowing through the fabric of the universe, and their motion has a cost. As these incredibly dense objects whirl around one another, they churn space-time, constantly losing orbital energy by emitting gravitational waves. This loss is exquisitely slow at first. Over timescales that dwarf the current age of the universe, the orbits imperceptibly shrink. A binary pair of white dwarfs that once took a century to complete a single orbit might, over 1 trillion years, see that period reduced to a decade, then a year, then a month. The inspiral is a slow, relentless tightening of a cosmic noose. In this far future, the galaxy will be a very different place. The era of brilliant starlight will have passed. The Milky Way will be a ghost of its former self, populated by these dark, degenerate remnants and the occasional failed brown dwarf. Yet, across this vast, silent darkness, a new kind of astronomy will be listening. Imagine a network of space-based gravitational wave observatories, successors to LISA, spanning not millions but billions of kilometers. Their lasers will measure distances with a precision smaller than an atom, tuned to listen for the low-frequency hum of the cosmos. And in that silence they will hear the chirps. These will not be the brief, catastrophic mergers from the universe's youth that we detect today with LIGO. These will be the final, drawn-out songs of systems that took 100 billion years to die. The signal from a merging decuple remnant will be a gravitational symphony of impossible complexity. It will not be a simple chirp from two black holes. It will be a layered signal, a cascade of tones. First, the tightest inner binary, perhaps two neutron stars that have been orbiting for eons, will finally spiral together. Their high-frequency whine will rise to a crescendo and then cut off in a final, sharp chirp. But that is just the first movement. The merger of that inner pair will have suddenly changed the gravitational center of the subsystem it was part of. This will destabilize the next level of the hierarchy. a wider binary consisting of that fresh merger remnant and another white dwarf will now find its orbit perturbed. Its own gravitational wave hum, previously too faint to hear, will suddenly amplify as its orbit tightens and circularizes. Decades or centuries later in the signal, that second binary will merge. This process could repeat, a chain reaction of inspirals working its way out through the system's ancient, frozen architecture. The waveform, the precise shape of the spacetime ripple, will be a forensic record. It will encode the entire hierarchical history of the original 10-star family. The masses of the merging objects will tell us what types of stars they came from. The orbital eccentricities and inclinations preserved in the signal will reveal the gravitational scars of past dynamical encounters, the kicks from long-vanished siblings, and the stability of their original orbits. By dissecting this gravitational fingerprint, future astrophysicists could potentially reconstruct the system's basic blueprint. They could deduce that the signal came from a system with a tight inner quadruple, 2 wider binaries, and a few single remnants all merging in a specific timed sequence. It would be like listening to the collapse of a meticulously engineered building, and from the sound of the crashing beams being able to deduce its original floor plan. In this profound way, the decuple system achieves a form of cosmic immortality. Its brilliant era as a beacon of light lasts only a few billion years. But its final era as a gravitational wave lighthouse could last for trillions more, as its dark remnants slowly whisper their way toward oblivion. These signals will be rare and precious, the final broadcasts from the most architecturally complex families the universe ever built. They will pulse across a dark galaxy, carrying within their subtle warp and weft the complete story of stellar chaos, gravitational order, and the enduring bonds that outlast the stars themselves. The last thing a decuple system ever does is tell us exactly how it lived. From that first confirmed point of light in Cassiopeiae to the silent gravitational whispers of a trillion-year future, our exploration of 50 strange truths has painted a universe far wilder than we ever dreamed. Decuple-star systems stand as the ultimate cosmic paradox, masterpieces of chaos sculpted by hidden laws of order. They force us to rewrite the textbooks on where planets can form, how stars can live together, and what true stability even means in a galaxy of constant motion. Every discovery, from the chemical tombstones of dead stars to the warped radio jets of microquasars, peels back another layer of their profound, beautiful complexity. These 10-star families are not astronomical freaks. They are natural laboratories testing the limits of gravity, magnetism, and time itself. They remind us that the cosmos thrives on dynamic tension, that from the greatest pandemonium can emerge pockets of exquisite, resonant harmony. Our own quiet solar system now feels like a serene backwater in comparison, a single note in a galactic symphony of roaring, chaotic chords. If this journey into stellar madness has reshaped your view of the heavens, show some love to the algorithm, smash that like button, and subscribe for more deep dives into the universe's strangest corners. Let us know in the comments which of these 50 discoveries left you the most awestruck. Was it the sky with 10 suns, the stellar zombies, or the thought of gravitational waves singing the system's story long after its light has died? Until our next adventure into the unknown, keep looking up and remember, the most profound order often hides within the most magnificent chaos. Our journey through 50 strange truths is not a final catalogue, but a snapshot of a science in motion. The hunt for these celestial families is accelerating, driven by observatories that will rewrite our maps of the stellar sky. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, or LSST, will soon begin a relentless 10-year scan of the entire southern sky. Its immense camera will capture the universe in motion, taking a complete picture every few nights. For decuple systems, this constant surveillance is a game changer. That chaotic, flickering point of light we struggled to monitor for years will be watched with unblinking eyes night after night for an entire decade. The LSST will not just find more of these systems, it will capture their full, frenetic light curves in exquisite detail. Its algorithms will sift through billions of stars, automatically flagging those with impossibly complex variability, the photometric fingerprints of 10 overlapping dances. We will move from studying a handful of confirmed examples to analyzing a statistical population, finally understanding how common or how truly rare these gravitational marvels really are. Meanwhile, the James Webb Space Telescope peers into the cradle of chaos. Its infrared vision cuts through the veils of dust that shroud young stellar nurseries. Where visible light telescopes see only a blur, Webb sees the architecture of infancy. It can directly image the warped, misaligned disks around young stars within these dense clusters, watching planet formation struggle against the tide of multiple gravities. It can detect the faint infrared glow of brown dwarfs hiding in the glare, finally solving the missing mass mystery for many systems. By studying the chemical fingerprints in the light of very young decuple candidates, Webb can determine if all the stars truly are siblings from the same cloud, or if some are adopted captives, telling us whether these systems are born whole or built by capture. The next decade promises to transform these rare curiosities into a well-understood class of celestial object. As our data grows from a trickle to a flood, the most exciting prospect is the boundary pusher. We have confirmed a system of 10 stars. What about 11 or 12? The hierarchical blueprint that allows 10 suns to survive could, in theory, support even more. We might find a system with a central sextuple core orbited by 2 distant triples, a family of 12. Or we may discover that 10 is a natural limit, a gravitational tipping point where adding just one more star guarantees rapid disintegration. Each new candidate system will be a test of our models, a challenge to our understanding of dynamical stability. The coming flood of data from Rubin and Webb will not just add to our list, it will force us to refine the very rules we have just begun to write. The story of decuple-star-systems is still being composed, its next chapters waiting in the starlight, ready for the next generation